right, sound check, sound check. Audio is coming in. Perfect. Let's check for video. Do I see my hand moving around over there? Oh. Actually, I don't. What is going on? Why is my camera inactive? Camera, what are you doing? Let me see if... Does that work? Okay, perfect. Now it's working. All right, unplug the headphones. And today is the day. Had to shuffle around my schedule a bit to make this work, but today's the day. This ends today. This is the end of the course. There will be one more little thing after this, just kind of a general overview for the exam and final advice and tips, as I've mentioned before. But then that'll be it. And then I can get back to panicking AP students of mine, and after that, maybe I can finally get back to working on a video game review and actually playing my video games. But without further ado, let's resume from where we left off last time. So, last time we did some calculus topics, and in addition to calculus, we also practiced with the unit vector notation, the standard unit vector notation that I showed in the first calculus topic we did 2 streams ago, the calculus basics stream. And we made it through, we looked at kinematics and force and work and energy. And that was pretty much where we stopped. We did a bunch of example problems that took longer than I had expected. We ended up going for like 6 hours. Hopefully it won't go for 6 hours today, but I cleared my schedule just in case. So, barring some sort of power outage or natural disaster or some other unexpected occurrence, today will be the end of the AP Physics C course, barring, again, that extra video that I'm planning to do sometime this coming weekend. So without further ado, let's begin. We were going to do momentum next, I believe. Okay, so momentum. Some momentum topics involving calculus. So really there's just 2 things that we want from momentum. There's really just 2 things. So for momentum, we know that the change in momentum is equal to the impulse, and we also know that impulse is equal to force times change in time. So if we rearrange this, we can say that force, if we divide both sides of, well, if we divide these 2 parts of the equation by delta t, we get force is equal to delta p over delta t, change in momentum over change in time. So that works when you have a constant force being applied to an object. You can figure out what that constant force is by just looking at how the momentum changes and dividing by the total time. But what if you have a variable force? What if your momentum doesn't change at the same rate per second? Well, in that case, you would just use a derivative. You would take your delta p over delta t becomes instantaneous force equals dp dt, the derivative of momentum with respect to time. If you had a momentum versus time graph and it had some sort of shape that wasn't easy to calculate the slope of, you could just get the slope of the tangent line at any given point, as long as you actually had momentum written as a function of time. and you'd get the slope of the tangent line, the instantaneous rate of change. This slope would be equal to the force that's being exerted on the object at that specific moment in time. Okay, rearranging this, actually, we don't have to rearrange it, we can just take the original version, delta P equals F delta T. Another thing you can do to calculate impulse is if your force is not constant but changes with time, then you can actually just do change in momentum, or impulse, is equal to the integral of force with respect to time. So you would just have, for example, a graph of force versus time. You get, again, some oddly shaped curve, and then the area under the curve between 2 points in time equals the change in momentum that occurs during that interval. So really simple stuff. Not much else that we can say here as far as momentum is concerned. There isn't a lot more calculus to show off. Let's go ahead and look at a couple of examples. It looks like I only have 3 picked out here, so we should be able to run through that topic pretty quickly. Which page are you on? Page 130 of my book. Is where they start. Okay, what is this question? Multiple choice number 6. What do you have? Okay, it says if J is the impulse of a particular force, if J is the impulse of a particular force, then what is dJ dt? What is dJ dt? And the answer choices are A, the momentum, B, the change in momentum. Whoops, capital B. The change in momentum. C, the force. And D, the change in the force. The change in the force. The change in the force. Okay, so yeah, we're looking at the change in impulse with respect to time. Impulse itself is not the same as the change in impulse. The change in impulse with respect to time. I guess we would just look at this. Yeah, if you know how to think about it, you should be fine. I can see a lot of people going for choice B and saying that it's the change in momentum, but that isn't true. If you divide by delta t, you have to divide by delta t everywhere, and that would mean that you have j over delta t, dj dt, is also is the change in, wait a minute. That doesn't look, let me think about this. So J over delta t. Well, first of all, this isn't a delta J, so that's the problem with this reasoning. So if you do this, J over delta t equals delta p over delta t, then you might convince yourself from this that dj dt equals dp dt, which would equal the force. But that's not true because, again, this is just j, this isn't delta j. If we want delta j, then I guess that would mean delta j would have to be F final wait a minute, F final times delta, I mean, I already know the answer is D. What I'm struggling with here is how to explain it in a way that makes sense to beginners. J is equal to F delta t. That's J at any given moment in time. If I want to calculate the change in J with respect to time, how would I define delta J? Because the delta t isn't going to be a constant. It would be, well, actually, for the same, hold on, for the same time interval, for the same delta t, yeah, I suppose this would be the case. And then divide by delta t everywhere, delta j over delta t. I don't know, this feels a bit too crude. I feel like having two forces multiplied by the same delta t is wrong, even though it is leading me to the correct result. Yeah, there's something wrong with the reasoning here. At least something that feels wrong. Would just equal F final minus F initial, which is just going to be called delta F. And yeah, dj dt equals delta F, the change in the force. Or dj dt equals dF. Yeah, I've never really thought about this one before. I mean, it's not every day that people ask about the change in impulse. Usually the impulse itself is the goal. But yeah, I'll think about this some more and post something in a pinned comment if I have anything more to say about this. But the bottom line here is that dj dt is equal to the change in the force and not the change in momentum. That's the thing to be careful about. Okay, so that was multiple choice question. The other two questions are not multiple choice, so what does this one have for us? Exercise 25 says we have two objects. 25 says we have two objects. Let's use this color. Two objects A and B collide. A has a mass of 2 kilograms and B has a mass of 3 kilograms. The velocities before the collision are v initial of A equals 15 I hat plus 30 j hat, while v initial B is equal to negative 10 I hat plus 5 j hat. After the collision, v final A is equal to negative 6 I hat plus 30 j hat. What is the final velocity of B? Okay, so it's a two-dimensional collision problem. Let me go ahead and see if I can draw the before and after pictures. So A, which has a mass of 2 kilograms, is moving 15 meters per second in the x direction and 30 in the y direction. So something like this. So that is object A. Object B is moving -10 in the x direction and +5 in the y direction. So -10 in the x direction, it's a 3 kilogram object, and it's moving -10 in the x direction and +5 in the y direction. So it's going to have an initial velocity something like this. So VA initial is equal to 15 I hat plus 30 J hat in meters per second. VB initial is equal to -10 I hat plus 5 J hat. Those are the velocity components. Excuse me, is this a bachelor's course? Kind of. It's a freshman college course, kind of, for high school students. It's an optional course that high school students can take to earn college credit. It's supposed to be equivalent to a freshman physics course for college students, except that high school students are meant to take it, so it can differ a little bit from from the standard college version of the course. I feel like I got the same question towards the end of last stream too. I guess I'm getting a lot of foreign students coming to these streams now. But yeah, it's very common in the United States and Canada and some European countries to take these courses. They're called advanced placement courses, or AP courses. So if you're interested in finding out more, you can definitely try and do a Google search on that. But I'm going to just continue with this problem. Now, where did I leave off? So we wrote down the initial velocities, and then we were told after collision, VA final, they actually called it V final A, but whatever, VA final is equal to, we've got -6 I hat and +30 J hat. -6 I hat plus 30 J hat. And we can go ahead and draw what that would look like. So that's the 2 kilogram object moving. I'll try and keep it to scale, but I don't know if it'll work. And then, oh yeah, I don't think I have enough space for this, but essentially it's going to be moving in that sort of a direction. So that's velocity A final. And their question is, what is the final velocity of B? So not really a calculus question here. It's just practice with the new notation in case you see it on the exam. You probably won't, but just in case. So we can just do conservation of momentum in the x direction and the y direction, and that would be it. So in the x direction, we can do M1, or rather MA, VAX initial. Actually, let me rewrite that because I already called them VA initial and VB initial. I'm going to do MA times VA initial X, there we go, plus MB times VB initial X equals MA times VA final in X, and then plus MB times VB final in X. In the Y direction, we would do similar. So we would do MA times VA initial in Y plus MB times VB initial in Y equals MA times VA final in Y plus MB times VB final in Y. There we go. And the rest is just plugging in the numbers that they gave us and doing a bit of algebra. So as long as you read this stuff correctly, VA initial in X is going to be positive 15. So this is going to be a 15. MA, of course, is 2 kilograms. And I guess I'll plug it in here as well. VA final, we've got negative 6 in the X direction. MB is 3 kilograms. VB initial in the X direction is negative 10. And B over here is 3 again, and VB final in the X direction is what you need to solve for. It's the only unknown in that whole equation, so it should be easy enough to do. Similar business over here. 2, and then VA initial in the Y direction is positive 30. And then for MB, that's 3 kilograms times VB initial in the Y direction is positive 5. And then 2 kilograms again. VA final in the Y direction is positive 30. And MB is 3 kilograms again, and VB final in the Y direction is the only unknown in that equation. So the rest is just algebra. You can take it from there. I'm going to go ahead and move on to the next one because I do not want this to turn into another 6-hour stream. I hope. Next one, I've marked it with a star, so I guess there's something about it. Oh, this one. Okay, this is reminding me that there's one other thing with calculating force. Okay. Yeah, this is an important problem that you might come across. Well, an important type of problem, I should say, not the problem itself. I'd be shocked if you got the exact problem to show up on the AP exam, but I've seen some things similar to this in the past. So let me go ahead and start a, new sheet. AP high school course, we do it in class 9 in India. Oh, wow, good to know. But yeah, this is supposed to be an AP course. This is supposed to be a college level course. Although, to be fair, I have successfully taught it to middle schoolers, so I'm not entirely surprised that you can do it in class 9 in India. I'm not entirely surprised by that. Let's go ahead and see. So it said a very flexible uniform chain of mass big M and length L. So they've drawn a chain and it's hovering just over a table, the ground, a table. It's hovering over a surface is the important thing. It has a length of L, big L, and a mass of big M, and it has a mass of big M. It's suspended from one end so that it hangs vertically, the lower end just touching the surface of a table. The upper end is suddenly released so that the chain falls onto the table and coils up in a small heap, each link coming to rest the instant it strikes the table. Find the force exerted by the table on the chain at any instant in terms of the weight of chain already on the table at that moment. So they've drawn like an after picture where some of the chain is coiled up into this pile that's already on the table, and some of the chain is still on its way down, still falling. Okay, so for this, we need to look at the force in a collision we said was equal to change in momentum with respect to time, and momentum typically changes in terms of velocity. We typically think of this as change in velocity over change in time multiplied by a constant mass. But you could also do it the other way. You could have a velocity at a specific moment in time, and you would need to multiply that velocity by the rate at which the mass is changing in time. That can also work sometimes, and this is what we need to do here, because it said, where did it go? Each link comes to rest the instant it strikes the table. The instant it strikes the table. So the velocity changes instantly. We don't really have a time rate of change for the velocity. Instead, over here, we need to figure out the rate at which the mass of chain is reaching the table per second. How much mass is hitting the table per second? That is what we're actually going to need to look for this time. So for this problem, you very rarely need to do this. I wouldn't expect this to be like the first thing to come to mind, but we would have to do dm dt times v equals the force at a given moment in time. So let's go ahead and see how we want to define all the relevant variables for this problem. So it said we need to find the force exerted by the table on the chain at any instant in terms of the weight of chain already on the table at that moment. So we want force as a function of time. Not surprising there. I mean, if you're taking a time derivative to calculate force, then your force should come out as a function of time. I'll call it f of t over there to remind us of that. So after some amount of time t has passed, well, then velocity ought to be a function of time as well. So f of t is equal to v of t times dm dt. Okay. And they said we wanted the force in terms of the weight of chain already on the table at that moment. So we need to also figure out how to define that. We're going to call it, we're just going to call it W. I hate using a capital W for weight, but just this once I'll let myself do it. So the weight of chain that is on the table at any given time t, what would it be? Well, let's see. So each segment of the chain is going to hit the table at a different velocity. The bottom of the chain is just going to hit the table with 0 velocity, and then the segment over that, like this segment over here, will fall a little bit and gain some velocity and hit the table at some speed. And then say I pick out this segment up here, it falls a greater distance and takes a longer time, so it's going to fall and hit the table with an even greater speed. And then of course the very top link of the chain will have fallen the farthest and will hit the table the hardest. Will hit the table the hardest at the highest velocity. So that will help us define our v of t, the velocity of the current segment of chain hitting the table at any given time t. What else? What else? The weight of chain that has already hit the table by time t. How can we figure that out? So we would need to figure out how much of the chain's mass has hit the table after t seconds have passed. Let's say after some time t, h worth of chain will have hit the table. H of the length will have hit the table. So I guess we'll define h of t. So h of t would be the amount of time it takes for this specific point on the chain to have hit the ground, and by the time this hits the ground, all the points beneath it have also hit the ground, or the table, not ground. So yeah, we can just determine the time from the highest segment of chain that has hit the table. And if I just go with regular kinematics, because each link in the chain is going to have the same acceleration g, it's just that they all have different starting points, so they're going to have different times and different final speeds. If I just do delta y equals negative h, and I use, let's do third equation of kinematics, Vy final squared equals, actually, maybe I don't want third equation. Let me think about this for a second. Vy final squared equals Vy initial squared plus 2 times acceleration is negative g times delta y. So that gives us Vy final is equal to the square root of Vy initial squared is going to be 0, and then 2 times negative g times negative h, that's just going to be 2gh. The negatives will cancel out. Okay, Vy final is square root of 2gh. That's not surprising. We see that a lot in physics. But we are going to need h as a function of time. Yeah, we are going to need h as a function of time. So to get that, we can just use the second equation of kinematics, delta y equals Vy initial times t plus 1/2 of negative g times t squared. That's a 0. And then negative 1/2 gt squared equals negative h. The negatives cancel out. And so we get h of t equals 1/2 gt squared. Okay, here we go. H of t equals 1/2 gt squared. So once we know the height of chain that has hit the table in some time t, we know the weight of chain that has hit the table, because we can just do the mass of chain on the table at time t is equal to the length of chain that has piled onto the table at time t multiplied by the linear mass density. If the full length of the chain has a mass m, then h over L is going to equal m over big M. If h is 1/2 of big L, then the mass would be half of the mass of the chain. Whatever fraction of the length h is, that same fraction of the mass will have dropped onto the table in that same amount of time. So I can do m equals, so if I rearrange this, I can just do m equals, just multiply big M over to the other side, and you have big M over big L times h. So m of t is h of t times big M over big L. And then the weight would be just taking the mass and multiplying it by g, so I'm going to write it as m over L times g times h of t, which is 1/2 gt squared. All right, this is looking good. I guess I could try and simplify and condense this, but we'll hold on to that for a second because I have a feeling some of these terms might cancel out. So Vy final we had is equal to square root 2gh. We're probably going to need to multiply that by dm dt. The force with which the chain is hitting the table at any given time is going to be equal to the speed of the current link of the chain multiplied by the rate at which the mass reaching the chain is changing with time. So we're going to do f of t equals v is equal to square root 2gh is equal to square root 2gh of t. Actually, I don't want to complicate it with a square root. Let's actually do first equation of kinematics. So Vy final is equal to Vy initial, which is 0, minus g times t. Yeah, Vy final equals negative gt. That's what I want to use. So we're going to have v at any given time is equal to negative gt times dm dt. dm dt, if I take the derivative of m of t if I take the derivative of m of t, m prime of t, that's going to be big M over big L times h prime of t equals m over L times h of t was 1/2 gt squared. If I take the derivative with respect to time, then derivative of t squared is going to be 2t to the 1, 2t to the 1 times 1/2 g, the 1/2 and the 2 cancel out, and we're just left with gt. Okay, m over L times gt, so that's m prime of t, so that's m over big L times gt. And then we can do, so they want the force in terms of the weight, so f of t versus w of t. If I multiply this out, actually, do I need to? It looks like I have 2 g's and 2 t's. I'm going to have a g squared and a t squared. I don't have the 1/2. Okay, yeah, let's multiply it out. So it's going to be negative m over L g squared t squared versus this is going to be 1/2 m over L g squared t squared. So f of t equals negative, it'll be 2 times w of t. It's going to be equal to negative 2w. Or if you want, just the magnitude of that force. If you don't want to worry about directions and stuff, the magnitude of the force of collision at any given time is equal to 2w. Now, that is the force of the collision. The question was asking for what? It said, find the force exerted by the table on the chain at any instant in terms of the weight of chain already on the table at that moment. So, it's the force exerted by the table on the chain. This is just the force of the collision. This is the force that the landing segment of chain is exerting on the table at any given moment in order to be stopped. The table is not only exerting enough force to stop the chain, but it also needs to exert enough force to support the weight of chain that's already on there. So the force in the table, the force that the table exerts, has to equal this stopping force plus it also needs to support the weight of chain that's already on there. So it's going to be 2w plus w is equal to 3w or 3w of t if you prefer. So yeah, at any given moment until the whole chain is finally done landing on the table, at any given moment in time, the table is exerting a force equal to 3 times the weight of however much chain has already landed. All right, there you go. This one, I would not blame most students for skipping it and doing easier questions if you saw this on the AP exam, because it is kind of a curveball. I mean, it'll probably start looking easy once you look at this multiple times, but it's just that you don't usually deal with momentum problems where you're worried about the rate of change of mass with time. Usually you're thinking about changing velocities, so this is just kind of, it puts you on your feet because it just gives you something that you're not used to working with. But that's the end of that question, and that's all I had to cover as far as momentum is concerned. Let's see what we have lined up next, and I should probably cross these off as I go so it's easier for me to find my place on my notes. Cross those off, and then on that other sheet, cross that off and cross that off. Okay, so next up is circular motion and gravitation. Not really anything significant for circular motion. I guess they could give you something where, like, an object in circular motion is accelerating with time, and you could probably do some sort of rate of change of the centripetal acceleration. But I don't think that's gonna give people too much trouble. I mean, we'll do some like rotational kinematics questions that would probably be the better way of looking at a circular motion question. You would probably want to look at it as a... Oh, wait, did my camera glitch out on me again? What is going on? Let me see. I think the problem is... Okay. Are we back? Do I see motion there? Sorry about that. I guess I'll have to make some edits for this one. Yeah, well, I'll figure out what I want to do about this. But all you really missed was just me writing the things that I was saying I was writing as I was going, so... Yeah, I don't know. I'll think about it. Great. This is not the issue I was expecting to encounter today. Of all possible issues, I would have thought something like a power outage taking out the stream would have been more likely. Fantastic. Worst case scenario, you can just freeze frame this page and go back and listen to everything I was doing for this problem and follow along with my voice. I just worked from mostly left to right this time. So hopefully it'll be easy enough to follow, and if need be, I can make an edit later. I'll just have to go back and look at the footage and figure out just how bad it was when it actually froze. But yeah, note to self, I'm just going to have to keep on looking back and forth at my screen because apparently today my camera doesn't want to work properly. Anyway, where was I before I noticed that camera issue? Oh, right, I was talking about circular motion. So if you have a circular motion problem where the tangential velocity is changing with time, I mean, we've already kind of seen that. It's whenever you have an angular acceleration, so I would just solve the problem from a rotational kinematics perspective instead. And if your angular acceleration isn't constant, well, that's easy enough to deal with. You would just use basic calculus. It's the same stuff that we did last time with regular kinematics. The equations of rotational kinematics work pretty much the same way. I think I have a few examples for those picked out. Not that we will really need them, but it doesn't hurt to do a few here and there. Anyway, before we get into rotational kinematics and dynamics, I would like to head towards gravitation. So for gravitation, the only calculus that was needed, we already did last time when deriving the other formula for gravitational potential energy, the negative big G mm over r, this thing. We showed where this comes from by using the integral definition of work and relating that to potential energy. So we already did this derivation, and there's not really much else that you need to do calculus-wise, at least not for the level of this course. So the only other thing that remains to be covered for gravitation is Newton's shell theorem, which we will then use later when we get to simple harmonic motion to talk about a special scenario. But Newton's shell theorems, so you've got two of them. Newton's shell theorems, we have two of them. And what do we mean by shell? Let me grab my spherical shell. So here we are. I don't know if it'll, yeah, it's too big to show the whole thing on screen, but that's okay, because what's more important is what happens when I open this up. This is half of a spherical shell. I can't even show a half of it fully on screen, but yeah, this thing is a spherical shell. It's just, well, this one is a really thick spherical shell. I'm mainly going to talk about thin spherical shells, but basically it's a bigger sphere with a smaller sphere carved out of it. Or you can also think of it as a hollow sphere, if that term from rotational dynamics makes more sense to you. So, the first shell theorem that Newton has goes something like this. If I have, for example, a big planet, and I want to figure out how much gravitational force is being exerted by this planet within an imagined spherical shell. If I imagine a spherical shell around it, it doesn't have to physically exist in the universe. It's just this bubble of interest you could think of it as. You can think of it as this: imagine a bubble around which, or within which, you're trying to figure out something physics-wise. So not a real physical tangible thing, just an imagined spherical shell, an imagined bubble surrounding a planet. So Newton's first shell theorem basically tells us that if you imagine a bubble of whatever radius, we'll call it radius r, surrounding an object or even a collection of objects, then Newton's first shell theorem basically says that the net gravitational force felt on the surface of this spherical shell, assuming everything is spherically symmetrical, is equivalent to if all the mass within this spherical shell were just concentrated at the center. So that's not really anything too surprising there. Basically, what this tells us is it doesn't matter if the mass of this sphere, the mass inside of this dotted sphere, is distributed unevenly. As long as it's spherically symmetrical, that's all that matters. So if you have, for example, the Earth, we know that like the density of different layers of the Earth are going to vary. We know, for example, that the crust has a higher density than the mantle. I would assume it's a higher density because the mantle is liquid while the crust is solid. And then the core has a higher density than the mantle and the crust. So basically, what Newton is telling us here with the first shell theorem is, as long as it's spherically symmetrical, you don't have to worry about the fact that the mass isn't evenly distributed across, I guess, this line going from the center to the outside. You don't have to worry about that as long as it's spherically symmetrical. You can just pretend that all of this mass, regardless of which layer it comes from, you can treat all of this mass as being at the center and calculate the net gravitational force at any point on the surface of this imagined sphere as if it were all at the center. So you would just do, it should surprise you, the force of gravity is just going to be big G, mass of the planet, mass of the object, over r squared. You would treat the full mass of the planet as being at the center. You don't worry about where each chunk of the mass actually is. So that one is probably something that people would have done anyway, even if they weren't aware of Newton's shell theorem. I mean, that's what we've been doing. It's just we never actually questioned it. We never actually questioned it. But I can imagine somebody probably had the question come across their mind. They probably went, wait a minute, wouldn't it be different if, you know, you calculated your distance from some parts of the Earth that are at higher density versus other parts that are at lower density? I mean, technically, the distribution of mass around the Earth isn't entirely even. But for the most part, we can get away with it. And we have been getting away with it. So that's the first shell theorem, not the most exciting thing. The second shell theorem is the more interesting one. So Newton's second shell theorem says, what happens if your spherical shell lies on the inside of an object? What happens if you imagine a sphere of interest somewhere inside the object? So if I have, again, a big planet, and now I want to figure out the gravitational force somewhere inside the planet at a distance r from the center of the planet. Well, Newton's second shell theorem tells us we can ignore the gravitational effect of everything outside of this sphere. Yes, there is mass out here, but we can ignore all of it, assuming, again, perfect spherical symmetry. Assuming spherical symmetry, we can ignore all of this and pretend that it has no gravitational effect, because if you do the calculus, and the calculus is complicated, like even if you've done calculus BC, you're not ready for the calculus needed to actually prove this. But if you do the calculus, you'll find that the total gravitational force due to every bit of mass in this outside part, it nets out to 0. And while we can't do the calculus, I can give you some intuition as to why that might be. So imagine yourself a spherical shell. We'll say that it's empty in here. We'll say that there's no mass in here. And let's say I want to figure out the force of gravity exerted by this outer shell. It doesn't even have to be on the edge of this outer shell. It could be at any point within this empty section. So let's say, for example, I want to figure out the net force at that point due to all the mass of this outside shell. It's going to be 0 because if you try and chop this into pieces, if you try to chop this into a bunch of pieces, if I try to chop this into, let's say I slice it here, and then we'll cut that into multiple slices there, and we'll do a slice here and a slice there, and a slice here and a slice there, and a slice here and a slice there, and we'll just keep making these cuts. Yeah, something like that. If I were to cut this into a bunch of little itty-bitty pieces, an infinite number of them, in fact, because, you know, calculus, Riemann sums, and all that, and I were to then take each of these pieces and calculate the individual forces of gravity due to each piece. What color do I want to use here? Let's use this light blue. If I wanted to figure out the force of gravity due to each of these pieces. So what about the force of gravity due to this piece? Well, this is a very close piece, so r is going to be low, the distance is going to be low, so I'm going to expect a lot of gravitational force in this direction due to this piece. Similarly, I'll have a lot due to this piece and a lot due to this piece, so I've got just a lot of gravitational force in this direction. I've also got a lot of gravitational force this way, and this way, and this way, and this way. I should actually be drawing them shorter, so yeah, these are going to be almost as long as that middle one. And these two should be shorter, and then those two should be shorter. Something like that. And the horizontal components, we'll say that this is my x-axis. I know it's a little bit slanted, but we'll say that's my x-axis and that's my y-axis. So the x components of each of these forces, well, they're going to cancel out, so I don't even need to bother with angling the forces. I'll just draw their y components, since those are the only components that matter. We've already canceled out the x components. So what's happening with the y components? Well, we've got a few big y components over here. There are a few parts of this shell that are going to contribute a lot of big y components in this positive y direction. But what we have even more of, even though the force of gravity due to these pieces over here is going to be lower because they're further away, even though these are going to have a lower force of gravity that they exert, even though these pieces over here exert lower gravitational forces, there's more of them. There's more pieces. If I draw another dotted line over here to separate what's, I guess, in the positive y versus the negative y relative to this location that I'm interested in, this original x that's now barely visible because I've drawn over it so much. If I were to look at the number of pieces that are above it versus below it, there are fewer pieces above than below. So even though the pieces above exert a stronger gravitational force on it, it turns out that the increase in the number of pieces, since the total number of pieces below is higher than the total number of pieces above, even though they each contribute a lower gravitational force than the pieces above, it turns out when you total everything out, it turns out to be completely even. It turns out that all of these y components do get canceled out. I know that's not really a proof, but I would hope at the very least that this gives you at least some faith that Newton's second shell theorem is correct. So the mass on the outside, as long as it's spherically symmetric, the mass on the outside of a spherical shell contributes no net gravitational force anywhere within that shell. If you've defined a spherical shell within which you want to figure out the force of gravity, you can completely ignore any mass outside of that shell. And that just leaves the net gravity to be due to the mass still within the shell. So over here, I said that this inside part is empty, but if we were looking at something like the Earth, let's say you wanted to go and figure out what's the gravitational force just when you reach past Earth's crust and you hit the boundary between Earth's crust and its mantle, you could do that. You would just do big G m over r, where big M over here is going to be just all the mass in this purple region. So the mass of the mantle plus the mass of Earth's core. That would be your big M in this case, and that would be your force of gravity. So maybe calling it big M isn't really best. I'll call it big M star, so that we don't confuse it with the big M that we had over here. So if big M is the mass of the planet, big M star is the mass of the portion of the planet that is still within a distance r of the Earth's center. That would be the net gravitational force experienced by a point on the surface of a spherical shell whose radius is smaller than the radius of the planet. Now let's go ahead and grab, I think I had 2 or 3 problems involving this. Let me go ahead and look through them. So it says they're on page 319. I know at least one of them has us looking through different layers of the Earth. Page 319. And yeah, this book doesn't really go in the order that I prefer. So in case you were paying attention to the page numbers I've been saying out loud and you're wondering why I'm jumping from the 100s to the 300s and back to the 100s again, it's because they put gravitation and energy further down the list from where I would put it. I teach energy earlier. This book, for whatever reason, likes to delay the topic of energy and gravitation and whatnot. So 319, here we are. We're looking at exercises 10 and 11 and problem 13. What do they have for us? Okay, yeah, they all involve the shell theorem. And problem 13 was, yeah, problem 13 was that problem. Perfect. Past me was actually thinking when choosing these problems. That is good. What color do I want to use? I guess I'll use this dark one first. Okay, exercises 10 and 11. So this first one says 2 concentric shells of uniform density having masses m1 and m2 are situated as shown in the figure. So they've drawn 2 shells. I know they're going to look like rings in this drawing, but they are just cross sections of shells. So here's one shell, and then there's a bigger one around it. remember, these are representations of spherical shells. And I suppose I can color them so that we don't get confused about where the empty space is and where the shells are. So the colored spaces have mass, the uncolored spaces do not have mass. Okay, they said that this inner one has a mass m1 and the outer one has a mass m2, and it says two concentric shells of uniform density. Concentric, by the way, means that they have the same center, in case that word is foreign to you. It says find the force on a particle of mass little m when the particle is located at r equals a, b, and c. So they've defined a couple of different distances. They've called this distance c. They've called this distance over here b. And they've drawn a distance that goes somewhere outside of both shells, and they've called that distance a. And it says, find the force on a particle of mass little m at each of those distances. Okay, so force of gravity at distance c is going to equal big G times, well, how much mass is actually inside, because we can ignore the outside according to Newton's second shell theorem. We can ignore the outside, so how much mass is left on the inside? Well, 0. There's no mass within a distance c from the center of these two shells. So this is just going to be a big 0. Okay, what about the force of gravity at point at B? I did these in the reverse order, but that's okay. The force of gravity at a distance B from the center of these two shells is going to be big G times, we can ignore all the mass on the outside, so that just leaves the mass on the inside, the total mass inside. If I were to picture a spherical shell of radius b over here, how much mass does it contain? It contains all of m1, and that's it. So it would be g times m1 times little m over, of course, the distance would be b squared from the center, equals whatever it is. And then what is the force of gravity at a distance a from the centers of these two spherical shells? That's going to be big G times, let's see, so if I were to draw a sphere of radius a, if I were to draw a spherical shell of radius a, we can ignore anything outside of it. Well, there's nothing outside of it, so that's good. And then first shell theorem says we just take the total mass inside. So m1 plus m2, we don't worry about how it's distributed as long as it's spherically symmetric, which is what the problem told us. It told us that the shells have uniform density, and uniform is definitely symmetric. Uniform is always symmetric, but you do not need to be uniform in order to be symmetric. So it's kind of like how all squares are rectangles, but not all rectangles are square. Same idea here. All uniform mass distributions are symmetric, but not all symmetric mass distributions are uniform. So Remember, the requirement for Newton's shell theorems is that it only needs to be symmetric. It doesn't need to be uniform. So big G, and then total mass is m1 plus m2 on the inside multiplied by the mass of the object divided by the distance squared, a squared. There you go. It's done. Really easy. You'll do more of this in the electricity and magnetism course using something that's basically the same as Newton's shell theorems, except it's for electric charge. It's called Gauss's law. So that is something you can look forward to if you plan on doing electromagnetism. Remember this because it's going to be brought up again in that course. In fact, it's going to be brought up again pretty early, like second or third unit, depending on how your teachers decide to cover the course content. Or maybe even the first unit, depending on how they define their units. But anyway, next problem says, show that at the bottom of a vertical mine shaft dug to depth capital D, the measured value of little g will be little g equals gs times, in parentheses, 1 minus capital D over capital R, with gs being the surface value. Assume that the Earth is a uniform sphere of radius r. Okay, so we're assuming a uniform density for the Earth. And the problem they are asking us about is this. So they have the Earth, and then they dig a mine shaft, and the depth of this mine shaft, they called it capital D. They called this capital D. And they want to figure out what is G at that depth. It's not going to be 9.8, so I guess I would call it G of R. So their question is, prove that G of R at that depth is equal to GS times 1 minus D over R, where big R, of course, is going to be the radius of the planet. And GS, that's the 9.8 that we're used to. GS is G surface. So it wants us to show that at the bottom of a vertical mine shaft dug to depth D, the measured value of G will be given by this equation. That's what we're trying to derive. That's what we're trying to prove. We are going to assume that the mass that we dug out of here and probably just piled up, over here, just outside of the hole, we're going to assume the effect of that is negligible. We're going to assume that has a negligible effect on our calculation. So what we want to do is just apply Newton's second shell theorem and give ourselves a shell of radius, well, let's see. So the full radius of Earth is big R, and the depth of this shaft is D. So what I want to do is I want to subtract this from this, and that would just be R minus D. So the radius of this shell is going to be R minus D. That will be this radius. I guess I don't actually want to draw an arrowhead for it because that would imply that it's a vector. Well, I mean, it is a vector. You could just call it a position vector if you wanted to. But anyway, so distance is R minus D. So we're going to have the force of gravity on an object, which we could call m times G of R, is equal to big G times, I'm going to call it the mass inside for now, times the mass of the object over the distance squared. The distance is r minus d, so over r minus d squared. Okay. The m's, the little m's cancel out, so it doesn't matter what the mass of the object is that you bring down to the bottom of this mine shaft. All that matters is how much mass is left under you once you're at the bottom of this mine shaft. I almost said mind shaft for a minute there. So how do we define the mass inside? Well, they told us to assume a uniform density. So the mass that's inside should be proportional to the volume on the inside. So we can do total mass of the Earth divided by the total volume of the Earth equals the mass inside divided by the volume inside. They should be the same ratio. The mass per volume should be constant. They said it was a uniform density that they wanted us to assume. So I can just do, let's see, I would do the mass inside is equal to the total mass of the Earth multiplied by the ratio of the inner to outer volumes. So m inside is going to be mass Earth times V inside over V Earth equals total mass times 4/3 pi inner radius cubed. So the inner radius we said was r minus d, so times r minus d cubed over the volume of the Earth is going to be 4/3 pi times the radius of the Earth cubed. Or I guess we could also just call it r because that's what we called it over here. Yeah, I didn't need the e, did I? Yeah, I did not need the e subscript over here. All right, the 4/3 pi cancels out, so that's all gone. What color should I switch to? Let's do this dark blue. It barely looks different from the color just above it. So we're gonna have the gravity as a function of r. Gravity as a function of r is going to equal big G times the mass inside is the mass of the Earth over r minus d squared and then the mass inside it was going to be the mass of the Earth times r minus d cubed over r cubed, so times r minus d cubed over r cubed. Yeah, there we go. G mass inside over r minus d squared. Mass inside is all of this. Okay, r minus d cubed and r minus d squared reduce, thankfully. So we get G mass of Earth over the r cubed. I'm going to split up into r squared and r, like this. And the reason for that is because g times mass of Earth over r squared over radius of Earth squared, well, that's g surface. G surface is g times the full mass of the Earth over r squared. We've seen this before. So I can rewrite this as g surface, which should amount to 9.8. And then r minus d over r over r is 1, minus d over r is d over r, and there you go, we're done. We've proven it. G at depth d is equal to, actually, come to think of it, I should have written it as g of d, as a function of depth, rather than as a function of r. Yeah, d would be the variable here. So yeah, g at depth d is 1 minus d over r times the normal gravitational acceleration felt on the surface of the Earth. And I see we're not having camera troubles anymore, so I'm going to hope that's a sign that that one mishap was the only mishap. Hopefully I won't have to do too much to correct it, if anything at all, but we'll see. Okay, next up we have this problem where we don't assume uniform density. So this next problem tells us, and I'm not going to do the whole problem, but at least outline how to do it. It says the figure below shows not to scale a cross-section through the interior of the Earth. So they've drawn the Earth, but they've highlighted 3 different layers: the core, the mantle, and the crust. So you've got the core, surrounded by the mantle, surrounded by the crust. And it also gives us some information. So it tells us that the mass of the core is 1.93 times 10 to the 24 kilograms, 1.93 times 10 to the 24 kilograms. And it has a radius of 3,490 kilometers, 3,490 kilometers. Then they have the mantle over here, which has a mass of 4.01 times 10 to the 24 kilograms. And it has an outer radius of 6345 kilometers. So inner radius 3490 kilometers to an outer radius of 6345 kilometers. And then finally they have the crust, whose mass is 3.94 times 10 to the 22, 3.94 times 10 to the 22 kilograms. And whose thickness is 25 kilometers. So it ranges from 6345 kilometers to 63, if I add 25 kilometers to that, that would be 6370 kilometers, which is 6.37 times 10 to the 6. I usually see it as 6.36 times 10 to the 6 for the radius of the Earth, but sure, 6.37 isn't that far off. Depends on who you ask. Okay, so it says, the figure shows not to scale a cross-section through the interior of the Earth. Rather than being uniform throughout, the Earth is divided into 3 zones, an outer crust, a mantle, and an inner core. The dimensions of these zones and the mass contained within them are shown in the figure. I decided to just write them out instead of writing them on the figure because that would have become really messy. The Earth has total mass of 5.98 times 10 to the 24 kilograms. So if we add these up, they should add up to 5.98 times 10 to the 24. And the total radius is 6370. Oh, if I had just read that, I wouldn't have had to calculate this, but adding 25 to a number isn't that hard, so it's fine. Ignore rotation and assume that the Earth is spherical. Part A, calculate g at the surface. Okay, so you would just take the total mass, right? Newton's first shell theorem. We don't worry about the fact that the densities are different at different layers. They're symmetric, so just treat all the mass as being concentrated at the center of mass and you're good to go. Part B, suppose that a borehole is driven to the crust-mantle interface, which I guess is also called the MOHO. What would be the value of G at the bottom of the hole? Well, I suppose we would have to let's see, so they said it's driven to the crust-mantle interface. So they're saying, what is the force of gravity over here between these first 2 layers, these 2 outermost layers? Okay, so I would just do, we can ignore the mass on the outside, according to Newton's second shell theorem over here. And we would just do the mass of the core plus the mass of the mantle. So I would just do G equals G times M core plus M mantle, and we leave out the crust, divided by this distance from here to here would be the, let's see, the crust begins at 6345, which is also where the mantle ends, so it would be 6345 times 1,000, because I would want to convert it to meters, so times 10 to the 3, and then that squared. And you can plug in those numbers if you really want to know what the value of G is, but I'm going to skip that. Part C, suppose that the Earth were a uniform sphere with the same total mass and size. What would be the value of G at a depth of 25 kilometers? So basically they're asking, what would the value of G be again at this same distance if we assumed a uniform density instead? That's pretty much what we did in this previous question. You could just plug in D equals 25 kilometers, or 25 times 10 to the 3 to convert it to meters, and divide by R equals, what, 6370 times 10 to the 3? Yeah, I would just use this formula, honestly, since we already did the work for it, just to save ourselves some time. But if you really had to do it from scratch, you could. That's not the most interesting part. Did I pick the wrong question? Because there was supposed to be something involving calculus here. Maybe it's the next question. Use the model of the Earth shown in the figure of the previous problem to examine the variation of G with depth in the interior of the Earth. Find G at the core-mantle interface. How does G vary from this interface to the center of the Earth? And then part B, show that G has a local... Yeah, this was the one. Okay, I picked the wrong problem, but at least it's the right diagram, so it's not that big of a blunder. It's not too big of a blunder. So it says use the model of the Earth shown in this figure to examine the variation of G with depth in the interior. Finding G at the core-mantle interface, it's just going to be this again. So we already did it. And then the second part of that question is, how does G vary from this interface to the center of Earth? So if you were to keep going deeper, how does it vary? Does it increase? Does it decrease? Does it increase sometimes and then switch to decreasing, or vice versa? How does it vary? For that, you need to do a derivative. For that, you need to do a derivative. Wait a minute. Oh, core mantle interface, not crust mantle interface. Okay, never mind. It's not this. It's not this. Okay, let's do it on the next sheet. Since this sheet is already out of space for us, let's do it on this next sheet. Okay, so on the core mantle interface, G would be big G times just the mass of the core. The core mantle interface is right here, where the core and mantle meet. Okay, so that would be G times M core, and that's it, over the distance from the center squared would just be the radius of the core, which is 3490 kilometers, so 3490 times 10 to the 3 in meters, and then that squared. So that is the first part of part A. And then how does G vary from this interface to the center of Earth? How does G vary from this interface to the center of Earth? So if I were to keep going even deeper, if I were to keep going to smaller and smaller distances r from the center until I actually hit the center, how does G change? Well, we could say G of r within the core, starting from the core's surface and going towards 0, or I guess you could define it the opposite way, starting from 0 and going out to the surface of the core, however you prefer to think about it. G of r is going to be G times whatever mass of the core is still inside. So if you stopped at a distance r that's less than the radius of the core, you would be invoking Newton's second shell theorem again, and you would only be taking whatever portion of the core is still inside and then dividing by whatever that radius is squared. This is assuming, of course, that r ranges between 0 and the radius of the core. This doesn't work once you get outside of the core, because then you have to consider the mantle and its mass and density instead. But this works up to 3490 kilometers. Okay. And how does it vary? Well, if I define the mass of the portion of the core that's inside at any distance r within this range, then I would just say I have a uniform density all throughout the core. Within the core, the density is uniform. So I would just do mass core in over total mass of the core equals whatever distance r over the total radius of the core. Wait, no, not radius, volume equals v inside over v of the core. There we go. And then that's going to be, if I define my v's, that's going to be 4/3 pi r cubed over 4/3 pi 3496 cubed. Wait, 96? Why did I write 96? It's 90. How did I copy that wrong? Brain malfunction moments. Anyway, 3490 times 10 to the 3, since we're converting it to meters, cubed. Okay, the 4/3 pi cancels out, just like it did in the previous problem that we did. And we would do, I'm going to multiply by the mass, by the total mass of the core, multiply it over to the right-hand side. So mass core inner equals the full mass of the core times r cubed over, I guess I'll call it r core cubed, just so I don't have to write all of that every single time. And if I take this and plug it in here, then I get g of r is equal to big G times the mass of the core times r cubed over r core cubed divided by that same r squared that we had before. And here is the fascinating thing. So r squared reduces with r cubed to a single r. All this other stuff is constant. So we have g of r is equal to g m core over r core cubed. All of this is constant. And the only variable here is r to the first power. It's a linear relationship. This tells us that the acceleration due to gravity within the core increases linearly from 0 until you reach the surface of the core, until you reach this boundary between the core and the mantle. The variation is linear. So if you were to take the derivative, you would just get, well, this stuff, gm core over r core cubed. Okay, so that is part A. Part B says, show that G has a local minimum within the mantle. Find the distance from the Earth's center where this occurs and the associated value of G. So the second part is asking us to show that there is a local minimum somewhere within the mantle. There's a local minimum for g of r. So g of r is actually going to be a piecewise function. G of r is going to be a piecewise function. We just did the part of it that works from 0 to 3490. But there are two more parts from 3490 to 6345 and from 6345 to 6370. So there are two more pieces of g of r that we need to take into account. So I guess I'll write it over here on the side. G of r is going to be a piecewise function of r, where from r equals 0 to 3490 kilometers, so from r equals 0 to 3490 kilometers, g of r is simply this, is g m core over r core. I can already see I didn't make this long enough, not enough space, times r. Oh yeah, and given what's about to happen, yeah, this is definitely not enough space. Oh no. This is going to be an utter disaster. I can already feel it. Hopefully that'll be enough, but I have my doubts. Okay, so here's where it gets messy. It's not too hard to figure out what to do if you're on top of like your density stuff, but it's just the algebra that comes out of it looks very ugly. It doesn't simplify very neatly, at least if it's going to go the way I'm thinking it's going to go. So next, we need to figure out what happens for r between 3490 and 6345. So r from 3490 to 6345 kilometers. That's probably not all that readable, but we'll work with it. So in this case, if I were looking at a spherical shell somewhere within the mantle but outside of the core, I want to again define g of r as big G times the mass inside divided by the radius of my spherical shell squared. So the next segment of g of r, let me use a different color for this, and come to think of it, let me adjust my lighting a little bit. Okay, that's better. I knew I forgot something. So if I want to find g of r now, it's going to be big G times the mass inside of this next shell that I've drawn, which is going to be mass of the core, all of the core, plus a portion of the mass of the mantle, only the portion that's on the inside. So plus mass mantle inner, or I'll just call it in for short, over the radius of my spherical shell squared. So that's going to be whatever goes in here, this next segment of my piecewise function. So the mass of the mantle that's on the inside, how much of the mantle is on the inside? Well, we're going to say mass of mantle on the inside as a fraction of the full mass of the mantle is going to be equal to the volume of the mantle inside divided by the volume of the mantle. I guess I should have called this volume mantle inside. And here is the part that some students might screw up if they rush. The volume of the mantle is going to be the volume of my spherical shell minus the core. You have to subtract the core out because, well, it's not part of the mantle now, is it? So mass of the mantle inside, I'm going to go ahead and multiply the full mass of the mantle over to the right. And what we're going to get is mass of mantle inner is going to equal something times the full mass of the mantle. And that something is going to be, well, the total volume of the mantle is going to be 4/3 pi times, I'm going to call it R mantle cubed, where R mantle is going to be the outer radius of the mantle, the 6345. So this is what I mean by R mantle. And then that's 4/3 pi R mantle cubed minus 4/3 pi R core cubed. So minus R core cubed, and so I don't have to write the 4/3 pi again. I'll just keep it outside of those parentheses, R core cubed. Okay, what about the volume of the mantle that's actually within this imagined spherical shell? Well, it's not necessarily going to be at 6345. It's somewhere between 3490 and 6345. So it's going to be 4/3 pi times whatever that distance is. Let me actually draw a dividing line over here. Yeah, so that we don't get those blending in with each other. So 4/3 pi, we'll just call it R cubed, minus, we're subtracting the core again, so R core cubed. This would be the volume of the part of the mantle that's inside of my spherical shell over here. 4/3 pi R cubed would be the full volume of the sphere, minus 4/3 pi R core cubed would just be subtracting the core out of that. So yeah, it's ugly. At least the 4/3 pi cancels out, so that's one saving grace, but otherwise this is quite hideous. And this we have to now plug in to here. We now have to plug this into here, and then we have to do some calculus on top of that. I don't even know if... Because if I put this into the numerator here, I'm going to have something with R cubed in it. Well, I suppose because everything else is a bunch of constants, you would eventually get... You'd get something over R squared, a bunch of constants over R squared, and then plus or minus, I think it's going to be plus, a bunch of constants times R cubed over R squared. So the R cubed and R squared will reduce to just an R. So you're going to have something over R squared plus something times R. And you're going to take the derivative of that and set it to 0. Yeah, that's too much for an AP problem. I would be shocked if they actually gave you something that time-consuming as a free response question. And as a multiple choice, forget it. There's no way this would be reasonable for a multiple choice. I'll work with it a little bit here, but I'm definitely not going to fully solve this problem. So we would have G of R, at least for this next part of the piecewise definition, is going to be G M core, G M core plus all of this, so M mantle times R cubed minus R core cubed over R mantle cubed minus R core cubed all over R squared. Oh boy. I can already see this thing is going to be quite the headache. Oh, actually, it looks like I might have 3 constant terms. So if I distribute... Okay, I'll move this denominator, this R mantle cubed minus R core cubed, I'll move it under M mantle, and then distribute that. Okay, so I'm going to, just for the sake of writing this in a more condensed form, I'm going to say M mantle over R mantle cubed minus R core cubed. I'm going to call this, what am I going to call it? Well, it's a mass divided by something proportional to a volume. I don't even know. What should I call it? Let's call it... Okay, let's just call it a random Greek letter. Let's call it beta. Let's call that beta, just so that I have an easier way to write this whole mess. So we've got G of R equals G M core plus beta R cubed minus beta R core cubed over R squared, which simplifies to, I'm going to group these 2 constant terms together, so G M core minus beta R core cubed all over R squared plus beta R cubed over R squared. That reduces to beta R. Okay, so that is G of R for this second segment. So G M core minus beta. Yeah, I don't even have enough space for it. I knew it. Cubed over R squared plus beta R. Okay, that's about as good as it's gonna get with the amount of space I gave myself. So they were saying what? We needed to find a place where the gravitational acceleration has a local minimum within the mantle. Find the distance from the Earth's center where this occurs and the associated value of g. So for finding maximum and minimum values of a function, one calculus technique we can use is finding the derivative and setting it equal to 0, or also finding the places where the derivative is not defined. And that also involves, by the way, checking like boundary points, especially when you're dealing with a piecewise function like this. You want to check, for example, at 3490, where it switches from this to this. You would actually want to check and compare g of 3490 kilometers versus the other points that you get. You'd also want to check g of 6345. But yeah, find g prime of r, which would be, let's see, so this is just a bunch of constant stuff over r squared, or you can also say it's times r to the negative 2, and then by the power rule, you multiply by negative 2 and decrease the exponent by 1, so that becomes r to the negative 3. So you would have negative 2 times the numerator again, gm core, minus beta r core cubed. And then it's times r to the negative 3, so that's over r cubed in other words. And then plus the derivative of beta times r is just beta, so plus beta. So that's the derivative. And where is it 0 or undefined? Well, it's undefined when r is equal to 0, but r is equal to 0 is not an option because this is only for r equals 3490 to 6345 kilometers. So we don't have to worry about r equals 0. So now we look for where g prime of r is equal to 0. So I would just subtract beta on both sides. I would do 0 equals, well, this stuff equals negative 2. Do I really have to write it all again? I guess I will. Gm core minus beta r core cubed over little r cubed. Is that still visible on the screen? Yes, it is. Plus beta, and then subtract beta on both sides and cancel the negatives. So we would be looking for where beta equals or I guess I'll also multiply the r cubed. Yeah, so we're looking for where beta r cubed. Let me try that again. For where beta r cubed equals 2 gm core minus beta r core cubed. Divide by beta and take the cube root, and whatever you get, whatever that r is, it will be either a maximum or a minimum. You would want to just compare that. You would want to compare to just take your g prime of r and plug in an r that is slightly less and an r that is slightly more than whatever you get over here, just to make sure that it's a true minimum. You would know that it's a minimum if g prime of r before this value is negative and after this value it's positive. If it's negative before, that's decreasing. If it's positive after, that's increasing. So decreasing before increasing means you've hit some sort of low point and you're turning away from it and rising back again. And yeah, you have to go through all the trouble of plugging in all of this for all of these betas. But there is a solution here. There is an actual number that you can get here, and in case you aren't sold on this idea conceptually that G has a minimum somewhere within the mantle, then let's think about that conceptually for a minute here. So when you are on the surface of Earth, of course you have the whole mass of Earth, and your acceleration due to gravity is proportional to all the mass that you have underneath you. If you start burrowing, if you start looking deeper into the Earth, well, there are two factors that are at play. You've got the factor of, since you're getting closer, the gravitational force is increasing, since force of gravity is, well, inversely proportional to r squared, so by reducing r squared, you're increasing the force of gravity, but also you're reducing the total mass of Earth that actually contributes towards the gravity as you get deeper and deeper beneath the surface of the Earth. Those two factors are in competition with each other, and it turns out that the reduction in mass factor outweighs the effect of decreasing the distance. We showed that earlier. Where did we do it? I know we did it somewhere over here. Where was it? Ah, yes, over here. So when you have an object of, when you don't have any change in the density, if you just dig deeper into that object, in this case this was the Earth's core, but it would still work on the outer surface of the Earth, at least until you hit the mantle. The acceleration due to gravity is proportional to the distance. The distance squared in the denominator gets completely canceled out. So the mass change factor is going to predominate over the radius change factor when it comes to how the force of gravity, and therefore the acceleration due to gravity, changes as you dig deeper. But then you get to the mantle and something changes. Then you get to the mantle and something changes where the force of gravity is actually going to hit a point where it switches from decreasing to increasing. First off, it's going to start decreasing. Well, no, hold on. It was decreasing. So you start from the surface of the Earth, and as you go deeper, because the acceleration due to gravity is now proportional to the distance, you're going to get a net decrease in gravity after all factors are accounted for. The decrease in mass causes more decrease in gravity than you get an increase from getting closer. And you continue to decrease and decrease and decrease. Even when you hit the mantle, this decrease continues, but at some point, that stops happening, and the reason for that is because of the difference in density between the mantle and the core. The reason that this happens is because of the difference in density between the mantle and the core. So you are getting less and less of the mantle's mass contributing to the gravitational force as you penetrate deeper and deeper through the mantle, but the mantle's density is a lot less than the density of the crust. Than the density of the core, rather. The mantle's density is lower than the density of the core, so you're losing a tiny bit of mass, relatively speaking, for every, 1,000 kilometers deeper that you go. You're losing some mass from the mantle that contributes to the gravity, but you're not losing it quickly enough to make up for the fact that you are getting closer to the heavier, denser core. So you're getting closer to this denser core, and eventually, once you get close enough, that actually starts to matter, and then getting closer to the core starts becoming more important than whatever mass contribution you're losing from the mantle. And that is where the acceleration due to gravity starts increasing until, of course, you hit the core itself, and then it goes back to decreasing, because penetrating further after you've reached the core means now you're losing mass from the core, and that is enough mass lost to make up for the effect of getting closer. You lose enough mass from the core that it decreases your gravity more than getting closer to the center would increase it. Hopefully that made some semblance of sense. Maybe rewind it and replay it a few times and think about it, but I think I've gotten at least the essential ideas covered for you. I think with what I've said, you should be able to piece together the rest on your own if it wasn't made super clear with my explanation just there. Now that we've got that taken care of, the last thing they wanted for the problem is to actually sketch a graph of the acceleration due to gravity. And for that, you would also have to find the third section, the g of r for when you're in the Earth's crust, which is going to be yet another messy problem. It's actually going to turn out uglier than what we have over here inside the mantle, so good luck with that. You can draw the graph if you want to, but I don't know, I think that's taking it too far. I think it's taking it too far. I would say maybe just plug it into a graphing calculator just to see what it looks like, and then leave it at that. If we were given simpler numbers, maybe I'd go for it, but this is too much of a mess. I'm going to call it quits on this problem here and move on to something more important. So we have done. Let me check with my notes and make sure I'm on track. I've done the shell theorems. I have done the shell theorem problems. Now we move on to rotational kinematics. Let's see, rotational kinematics I'm probably not going to spend too much time on because we've already done a lot with regular kinematics and it's pretty much all the same. I'll just pick a few good ones, maybe at least go over the problem statements and note anything noteworthy about the problems and just leave the rest for you guys to do on your own. We've got page 171. Let's see. No multiple choice. It looks like we begin with exercises. First off, we have this one that says the angle turned through by the flywheel of a generator during a time interval t is given by, they use phi instead of theta, but I'll just rewrite it as a theta. Theta equals AT plus BT cubed minus CT to the fourth. Where A, B, and C are constants, what is the expression for its angular velocity and angular acceleration? Like, that's it. You take the first derivative you take the second derivative, you're done. Well, might as well do it since it's quick. So omega is equal to d theta dt, or theta prime if you prefer, or theta prime of t even, is equal to derivative of at is just a, plus derivative of bt cubed is 3b times t squared. It's all just power rule, minus 4ct cubed. All right, and then alpha is equal to d omega dt equals derivative of a constant is 0 plus derivative of 3b t squared. T squared has a derivative of 2t, so 2t times 3b is 6b t. And then minus 4ct cubed, derivative of t cubed is 3t squared. 3t squared times 4c is 12ct squared. And that's it. You're done. Nothing too surprising there. Next up on my list was... this one says a wheel rotates with an angular acceleration alpha z given by... so this next one says alpha z is equal to 4at cubed minus 3bt squared. Now, some of you might be wondering, what's this z about? Well, basically, if you draw something on the page where its angular acceleration is in the counterclockwise direction, then by the right-hand rule, you would end up with your thumb pointing out of the page, which is the positive z direction. That is not something you have to worry about for the AP exam. For the AP exam, anything involving the direction of rotation, whether it's for angular velocity, angular acceleration, angular displacement, or even torque or angular momentum, all of those will strictly be defined in terms of clockwise or counterclockwise. You do not have to worry about the right-hand rule definition for the directions of those vectors. And if you don't believe me, I guess we can look it up real quick in the course description. Let's see, Google AP Physics C course and exam description. And let's see, it should be that second link, I think. No, was it the first one? Yeah, that's the first one. It's the PDF file. Okay, let's find it. Let's switch over here real quick. Okay, so it's probably going to be under... torque and rotational dynamics. Where is it? I know there's a note for it somewhere. They even highlighted it somewhere. Okay, I think this is it. Boundary statement. AP Physics C Mechanics expects students to be able to mathematically manipulate the magnitudes of angular momentum, angular velocity, and angular acceleration using vector conventions. However, the directions of said vectors will not be assessed on the exam. Descriptions of the directions of rotational kinematics quantities for a point or rigid body are limited to clockwise and counterclockwise with respect to a given axis of rotation. There it is, straight from the horse's mouth. Their statement, not mine. Their statement, not mine. I'll keep this open. We're probably going to need it at some point again, I'm sure. Maybe. Who knows? But yeah, we'll keep it open. Anyway, back to my document camera. So the question was, a wheel rotates with an angular acceleration given by that equation right there. where t is the time and a and b are constants. If the wheel has an initial angular velocity omega 0, write the equations for the angular velocity and the angle turned through as functions of time. All right, easy enough. You just integrate twice. So you integrate the first time, omega equals the integral of alpha, or alpha z if you prefer, with respect to time, equals, let's see, integral of 4at cubed minus 3bt squared. Oh, I just realized they gave us some really nice numbers. That's going to be integral of t cubed is t to the 4 divided by 4, which cancels out nicely with that 4 we have over there. So that's a t to the 4 minus t squared becomes t cubed divided by 3. So that's going to cancel the 3 that we have over there, and that leaves us with b t cubed, and of course plus a constant. Omega of t equals a t to the 4 minus bt cubed plus a constant. Now, they also said that the wheel has an initial angular velocity of omega 0. So that tells us that omega of 0 equals omega 0. So a times 0 to the 4th minus b times 0 cubed plus c is equal to omega 0, so this cancels out, or not cancels out, it's a 0, and that's a 0. So c is equal to omega 0, so omega t, properly this time, is a t to the 4 plus, or rather minus b t cubed plus omega 0. All right, and integrate this to get theta. A wheel rotate, and they did say the wheel has initial angular velocity omega 0. They want the angle turned through. I mean, I guess that means they don't want you to find the plus c once we get theta of t. Not that we have any way to calculate it otherwise. But yeah, theta of t is just going to be the integral of omega of t with respect to time, so we just integrate again. Equals, let's see, a t to the 4 becomes t to the 5 over 5, so that's 1/5 a t to the 5, and then minus, let's see, t cubed becomes t to the 4 over 4, so that's minus 1/4 b t to the 4, and then plus the integral of a constant is the constant times the variable, and then plus some arbitrary constant. And yeah, I guess because of the way they worded it, the angle turned through, I guess what they really want is delta theta as a function of t, which would not require you to find c. So you could just turn this in as your answer if you saw this on the AP exam. I would imagine they would word it more clearly. But without any further information, we can't say anything about c, except maybe if the problem was worded a little bit more clearly, maybe we'd have reason to just assume that it's 0. And that is all there is to that problem. Really simple stuff. What was the other example I wanted to do? Exercise 32. What do you have for me? It says an object moves in the xy plane such that x equals r cosine omega t and y equals r sine omega t. Here, x and y are the coordinates of the object, t is the time, and r and omega are constants. Okay, let's start that over on the left-hand side of the page. So we have x equals r cosine omega t, and y equals r sine of omega t. So yeah, it says here x and y are coordinates of the object, t is the time, r and omega are constants. Part A says eliminate t between these equations to find the equation of the curve in which the object moves. What is this curve, and what is the meaning of the constant omega? Okay, so eliminate t between these equations. If I eliminate t, so how would I eliminate it between x and y? All I would have to do is just square both sides, because then I'd have a cosine squared and a sine squared that I could add to 1. So I could do x squared equals r squared cosine squared of omega t, and y equals r squared sine squared of omega t. And I could, y squared, and then add x squared to y squared, x squared plus y squared equals r squared cosine squared plus r squared sine squared. I'm going to factor out the r squared, and then we get cosine squared omega t plus sine squared omega t. It's been a while since we've seen this, but I would hope that you would remember what this is. Cosine squared plus sine squared is equal to 1. So we just get x squared plus y squared equals r squared. And what is the shape of a curve that is defined by this equation? It would have to be a circle. This is the equation of a circle of radius r. Now it said, what is the meaning of the constant omega? Well, it got eliminated, so did it ever even matter? That's kind of what they're asking. What is the meaning of omega over here? The higher omega is, the faster x and y are going to cycle, right? If you're doing cosine of t and sine of t versus cosine of 2t and sine of 2t versus cosine of 3t and sine of 3t, and so on and so forth, if you change the number by which you multiply t, then what you're doing is you're increasing how quickly x and y change. So omega is defining how quickly the object moves around this circular path. And also, the other giveaway is, well, it's called omega, which you would naturally associate with angular velocity, I would hope. So that's your other hint. Part B says differentiate the equations for x and y with respect to the time to find the x and y components of the velocity of the body, vx and vy, and then combine vx and vy to find the magnitude and direction of v. Describe the motion of the object. So now they want us to find vx and vy. So much for just describing the problems and moving on. Vx is going to be dx dt. Derivative of r cosine omega t is negative r sine of omega t times the derivative of omega t by the chain rule. So times omega. I guess I should have made more space for it, but negative omega r. Yeah, negative omega r sine of omega t. And then vy is going to do something similar. Derivative of r sine omega t is going to be r cosine of omega t. Derivative of sine is positive cosine. And then times the derivative of the inner function, so times derivative of omega t is just omega again. So negative omega r sine omega t and positive omega r cosine omega t are your velocity components. They said to combine Vx and Vy to find the magnitude and direction of V. So combine them to find magnitude and direction of V. Well, we can just do Vx squared plus Vy squared equals, it would be omega squared r squared sine squared plus omega squared r squared cosine squared. So we're just doing Pythagorean theorem here to combine vector components, and we get omega squared r squared is a common factor that I will pull out, and then times sine squared plus cosine squared. We've seen this before, that's just a 1. So v squared equals omega squared r squared, which means v is equal to omega times r, or r times omega, however you want to define it. And then they also wanted the direction, so to get the direction, I would do tangent. I would do tan inverse of Vy over Vx would be theta at any given time t. So Vy over Vx is going to be omega r cosine omega t, omega r cosine omega t over negative, whoops, hold on, no, that equals tan inverse of omega r cosine omega t over negative omega r sine of omega t. The omega r's cancel out. Wait, cosine over sine? Huh. Okay. Well, this is gonna be negative 1 over tan, interesting. Tan inverse of negative 1 over tan of omega t. Very interesting. So if I were to draw a right triangle here, and I were to say this is the angle omega t, and then this would be, and we'll say that this radius is 1, and that would make this have a length of cosine omega t, and this would have a length of sine omega t, then cosine over sine would be the tangent of this opposite angle, which is going to be 90 degrees minus omega t, which would be pi over 2 minus omega t. So this angle over here would be pi over 2 in radians minus omega t. So then this is going to be tan inverse of negative 1 over tan of omega t. I mean, I understand what it's hinting at because it's talking about uniform circular motion here. I understand what it's hinting at. What it's hinting at is that the velocity is going to be perpendicular to the radial direction. That's what it's hinting at. I'm just trying to figure out how to connect that conclusion to what we have so far. How do we go from here to that conclusion? So, negative 1 over tan of omega t. So we've got this angle, and then we need to take tan inverse of the negative of this angle. Well, no, wait. Tan inverse of, hold on, let me think this through. So the tangent function has the property where where tan of the negative of an angle equals the negative of the tan of that angle. And this property still applies to the inverse tangent, so I can say that this is going to be negative tan inverse of 1 over tan omega t. So that's negative of pi over 2 minus omega t. That is to say, it's the negative of pi over 2 minus omega t. That is to say, if I distribute the minus sign, that is to say, it is omega t minus pi over 2. Okay, so let me draw a hypothetical circular path here. And let's say at some point t, it's over here. And the way x is defined as r cosine omega t, while y is defined as r sine omega t, that tells me that we start over here on the right-hand side. Because then, at time 0, x would be equal to r times cosine of 0. That's r times 1. It would be positive r, in other words, while y would be r sine of 0, y would be 0. So if this is my x-axis and that's my y-axis, x would start over here at positive r, and y would start at 0. Okay, and then that means my theta is defined like this, theta, which equals omega times t, would be defined like that. And then they're saying the direction of the velocity is omega t minus pi over 2. So it's going to be 90 degrees behind wherever theta is. So if theta is this way, then subtract 90 degrees from there. It's saying subtract 90 degrees from this. So if I go 90 degrees behind here, oh, wait, no, theta would be if it's, wait a minute. Yeah, if theta takes me to here, then theta minus 90 degrees would give me this direction, so it would be this way. So that's telling me that the direction of the tangential velocity is like this. Is that true? No, that is not true. Something is wrong here. Something is wrong here because it should be the exact opposite direction. Well, I wasn't expecting this problem to have this big of a twist. I looked at it a few days ago, and when I added it to the list, I thought it was going to be quick and simple. But yeah, I must have messed up somewhere. I must have missed a negative sign somewhere around here. Either that or I just did something wrong with my assumptions about tan inverse and the negative sign. Yeah, I don't know. Well, this isn't really the most important part of this problem, so I'm just going to move on, and I'll think about this later and see if I can offer some insight in a pinned comment or an extra video or something. But for now, in the interest of time, I'm just going to move on. So next part of the question was differentiate Vx and Vy with respect to time to obtain the magnitude and direction of the resultant acceleration. So if I differentiate again, if I differentiate my Vx and Vy, which were up here, if I differentiate these again, then I get acceleration in x equals, let's see, derivative of sine is cosine, and then times an omega because of the chain rule, so that gives us negative omega squared r times cosine omega t. And then acceleration in y is going to be derivative of omega r cosine omega t. Derivative of cosine is negative sine, and then times an omega because of chain rule, so that's going to be negative omega squared r, and it becomes a sine of omega t. Okay, there we go. And for the magnitude, you would just square both of these and add them, very much like what we did over here, Vx squared plus Vy squared. We do the same thing here. Ax squared plus Ay squared. We've seen this twice before now. The cosine squared and sine squared will cancel out, and we get a total is just going to be negative omega squared r. It's going to be negative omega squared r. And as for its direction, well, it's going to be the exact opposite of x and y, right? Ax is going to be a negative constant times this r cosine omega t. Well, that's x. So it's always the opposite direction of where your x is. If x is positive, ax is negative. If x is negative, ax is positive. Similarly, when y is positive, ay is negative, and when y is negative, ay is positive, because ay is just negative omega squared times this part right here is just y. So that tells me that the acceleration is always opposite in direction to the position. That tells me acceleration is always towards the center at any given time, which is consistent with what we figured out a while ago, that this is uniform circular motion being described here. So yeah, I guess we did end up doing calculus with uniform circular motion after all, even after I said we weren't going to do much with it. All right. So I can check those off the list. And we have another one over here that says the angular position of a point on the rim of a rotating wheel is described by theta equals 4 radians per second times t minus 3 radians per second squared times t squared plus 1 radian per second cubed times t cubed, What is angular velocity at t equals 2 and t equals 4? What is average angular acceleration for the time interval that begins at t equals 2 and ends at t equals 4? And what is instantaneous angular acceleration at the beginning and end of this time interval? Okay, I'll just write it down for you, but I think this is easy enough that you guys can tackle it on your own. So this next one, it gives you phi, I'm just going to call it theta because that's what we're used to, is equal to 4t minus 3t squared plus 1t cubed. And the questions are, what is angular velocity at time 2? Angular velocity at time 4? Average angular acceleration between times 2 and 4, 2 to 4. And then part C says, what is the instantaneous angular acceleration at each of those times? So alpha of 2 and alpha of 4. Those are all the things you have to find. Pretty easy, just take a derivative once and plug in 2 and 4. To get the average angular acceleration, you would just take your omega of 4 minus omega of 2 divided by 4 minus 2. Pretty simple. You don't need calculus for that. Well, I mean, I guess you needed calculus just to get these two omega values, but you knew how to do this before calculus is what I mean to say. And then to get angular acceleration at specific moments in time, instantaneous angular acceleration, you would just take the derivative again. You take a derivative once to get omega of t, take the derivative again to get alpha of t, and you're good to go. So that is all we will say as far as rotational kinematics are concerned. We're almost at 3 hours. Oh God, it's a good thing I cleared my schedule today. So now we move on to rotational dynamics. Let me cross this out and let's see what we have here. So first some topics and then we'll look at some problems. Let me put this aside for a minute. Already filled that side of that sheet. Let's grab a new sheet. All right. So some things that we can now do with calculus that we couldn't do with algebra alone. So let's redefine our equations for center of mass and moment of inertia. So center of mass, the way we did it algebra based was we did the x and y coordinate of the center of mass would just be calculated by taking the mass at each point times its position. We would take each point, multiply it by its position, and then for however many masses you had, you would take that total and then divide it by the total of the masses. And this works great when you can divide your mass distribution into a bunch of individual points, but what if you have a continuous mass distribution? What if I have an object that has mass at several points, and what if that mass is distributed unevenly? What if very simple example, what if I had like a stick whose mass or whose density changes as you go further and further along the stick? Maybe it has like, I don't know, a metallic layer on top of it that gets thicker and thicker as you get closer to the end. So it has like some sort of starting density over here, rho 0, and its density just increases, let's say linearly, for example, as you go further and further. The proportion of, I don't know, metallic casing around this thing increases. So by the end of it, you have rho equals rho 0 times 1 plus, I don't know, something times L. Let's call it K, a constant K times L. How do we deal with a situation like this? Well, we can just do Riemann sums. We can chop this into tiny pieces and calculate the sum of the sum of, I guess they would be called moment contributions. Each of these mx's would be called a moment. And we could just write down a formula for the sum of these moments and then divide it by the sum of all of these masses. And then we would get at least the x position of the center of mass. If we had to do it for y, if this was a more two-dimensional object, we could repeat the process for y. So let's see, how would we go about doing this? So I would say, of course, I would have to define where my x begins. I'll say that's my x equals 0 line. And then at some point over here, if I just take one random thin piece of this thing, I will say that it has a small proportion of the total mass, which I would call dm. Instead of saying that it has a mass m, I'm going to say it has a very, very tiny change in mass dm. What do I mean by a change in mass here? What I mean is a change in the running total mass. So basically, you would start with a mass of 0, and as you went along from left to right, you would add more and more of these little tiny delta m's, or rather dm's. You would add more and more and more of them as you go on. And yeah, the delta m is, you could think of it, or dm, is a change in the total mass that you've counted so far as you move from left to right. Anyway, so this dm is going to also have a change in length. It's going to have a tiny length that I would call dl. And whatever that tiny length is, there's going to be a density at this point, and if I multiply the density by the length, I guess I should have called this lambda instead of rho, but we'll go with rho. We'll say rho over here is density as mass per length, as mass per unit length. Density as mass per unit length. Usually the symbol that textbooks like to use for length density is Greek letter lambda, which is what I should have used if I was thinking ahead. I probably would have done so, but we're in too deep now, so we'll just keep it as a rho. So you would take your density per unit length times your length, in this case times a very, very tiny bit of length, dl. And that would give you your dm. Now the nice thing here is that for a very, very small change in length, the density is going to be constant. Yes, the density changes as L changes, but if L doesn't change very significantly, if it only changes by an infinitesimal amount dl, then you can say it's approximately constant for at least the amount of length that you cover when crossing this small bit. So with that defined, we can now take this dm and multiply it by x. We can take this and multiply it by x, and that will be one of these many little contributions that we would have in the denominator. And in order to sum all of them up, well, we can't use a sum anymore. Instead, we would need to take an infinite number of these, so that calls for an integral. We would just say, instead of a sum of discrete mx's, instead we have an integral of x dm's. And we would just integrate from x equals 0 to x equals, I guess I would define this as capital L, the full length of the rod. Sometimes it'll be given to you as a number, but if it's not, it's okay. You can just use symbols for your integration bounds. And that gives us at least the numerator of our center of mass. Or rather the x-coordinate of our center of mass. What about the denominator? What about the total mass of this thing? Well, if there was just a constant length density, then I would say the total mass is just that constant density times the total length. But I don't have a constant density. So I'm going to have to, yet again, do an integral. And luckily, the integral is very similar to what I have in the numerator. So what I can do is I can take the density of a bunch of individual pieces of mass dm. I can take the density of individual pieces, multiply them by tiny bits of length so tiny that their density is very approximately constant. Calculate the mass of that piece, move on to the next piece and add it to the total, move on to the next piece and add it to the total. Yep, we've got mass as a Riemann sum, so we would just do, in this case, all we're adding up is a bunch of dm's. All we're doing is adding a basically infinite number of dm's. That's an integral, starting, of course, from 0 to L, just like the top integral. And that's it. If you want the y position of center of mass, and if you had a three-dimensional object, the z position, you would follow the same pattern. I guess maybe y would integrate from 0 to h, some sort of height. And then the denominator is just the integral of the dm's. And I guess we would have to distinguish the dmx's from the dmy's. They might be defined a little bit differently. So yeah, you would just have to make sure you check your integration bounds, and you might define your dm's a little bit differently in the x versus y direction, because you could have an object where like the mass density varies differently in the x direction from how it varies in the y direction. What would be an example of that? Let me think. An object where the variation in the x direction is different from the density variation in the y direction. Oh, I know. A book. So if I were to think about how the density of this book differs as I move along here versus moving along, well, here. As I move along here, I'm moving through cardboard, which is going to have a different density from if I'm moving here. I'm moving past the cardboard to paper and then back to cardboard again at the end. Very tough cardboard. But yeah, you would have different density functions in the x direction versus the y direction. I know this is a very crude example because in this direction the density is basically uniform, unless you want to really compare the densities of all these different colors of ink and take that into account. I would say that's taking it too far, but for the most part the density is constant as you go across here, but variable as you go here. So yeah, that would be an example of something where your dm's might be different in the x direction versus y direction. But there it is. It's just integral of x dm divided by integral of dm. That is how you find the x, y, and potentially z coordinates of center of mass. Your dm's are always going to be some sort of density times a dl or dA or dV, depending on whether you're talking about length, area, or volume densities. And that's basically it. So I guess let's go ahead and do this since we have an example over here. We might as well go ahead and do this integral and hope that it's nice to us. So x of the center of mass is going to be, we don't really have to worry about a y for this problem. It's going to be integral from x equals 0 to x equals L of x dm. Well, x at any given point, so at this random point over here, x would be at a distance of, we'll call it little l. Yeah, so I can either redefine my x as a little l, or I can redefine dl as being equivalent to a dx. Either way, the point is I'm trying to get my variables to agree with each other so that I can actually do the integral. So don't be too taken aback by that. dl and dx, I mean, a tiny change in L along this rod-like object is basically going to be the same size as a tiny change in X. So dl and dx are completely interchangeable. You can use one or the other, and actually, if I called this the L-axis instead of the X-axis, that also works. If I define L as being 0 over here and increasing up to big L, I think that's what I would actually rather do. But I've already called this x of the center of mass. Okay, we'll just continue with x. This is probably not what I should be getting hung up on right now. So integral from 0 to L of x times dm. dm is going to be rho, which is rho 0 times 1 plus kl, or rather kx, since L is equal to x. Times dx. Yeah, so I just substituted dm is equal to rho dl, where I replaced the L with an x and the dl with a dx. completely equivalent expression, nothing illegal has been done here, and then divide by integral from 0 to L of rho 0 plus kx dx. Basically copy over everything that you had up here except for that front x, which can sometimes change things quite dramatically. So don't underestimate this difference. Oh, and by the way, no, you cannot cancel out this stuff and just have the integral of x on top. You can't do that. So if you're thinking of taking a shortcut, think again. It's not going to work. Unless you like getting wrong answers, that is. Okay, so I'm going to distribute the x, so I get integral from 0 to L of rho 0 x plus kx squared dx. And then in the bottom, I can just go ahead and integrate the integral of rho 0 with respect to x is rho 0 x. And integral of kx, the k is a constant, and then integral of x is x squared divided by 2, so 1/2 kx squared. And then that's going to be evaluated from 0 to big L. Over here, if I go ahead and integrate, I'm going to have rho 0 x becomes 1/2 rho 0 x squared, and then kx squared, the x squared becomes x cubed divided by 3, so that's 1/3 k x cubed, and then evaluate that from 0 to L. All right. So if I plug in L over here, I get 1/2 rho 0 L squared plus 1/3 k L cubed, minus if I plug in 0, then I get 1/2 rho times 0 squared plus 1/3 k times 0 cubed, so just minus a 0. That's nice. And then in the denominator, we've got rho 0 times L plus 1/2 k L squared from plugging in the upper bound. If I plug in the lower bound, if I plug in 0, that's minus. Lower bound gives me 0 plus 0, so it's a minus 0 again. Well, that's nice. We didn't have to do twice as much work. And can I simplify this at all? I guess I can factor out an L, but that's about all I can do. So yeah, I can cancel one L everywhere, and that leaves me with 1/2 rho 0 L plus 1/3 k L squared over rho 0 plus 1/2 k L. And that would be the x position of the center of mass. Let me see if the units actually make sense here. So rho, or rather rho 0, is going to be in units of kilograms per meter, or whatever mass units you want to use per whatever length units you want to use, but I'll go with kilograms per meter. So kilograms per meter times meters gives me kilograms, plus we have meters squared. Wait a minute, that doesn't make sense. Would the k be unitless? Yeah, k would have to be unitless over here. Wait, is the K really unitless though? So we would have to do density. No, K can't be unitless. It would have to be in, let's see, because this needs to work out to kilograms per meter. So if this is going to be in kilograms per meter as well, then the 1 isn't going to have any units to it, which means whatever units K are, they have to cancel out with the units of L. So K is going to be in units of inverse meters. Yeah, K is going to have to be in units of inverse meters. So we would have kilograms plus... No, that doesn't work either. What am I doing wrong here? What am I doing wrong here? This whole thing in the parentheses needs to be unitless. Let's see, so... And whatever this integrates to, it needs to be in units of kilogram meters. Let's see. So I've got kilograms per meter times... Oh, I know what I did wrong. I didn't distribute the row 0 correctly. Row 0 times 1 plus KL should be row 0 plus row 0K. Yeah, there needs to be a row 0. Okay, let me do that in a different color so that it's easy to spot. Yeah, multiply this by row 0, multiply this by row 0. Well, fortunately, this is a constant, so it's not going to change our integral. I just have to multiply it into every term that should have contained it, and then that will be the fix. And wait, no, I should have written it over here. Okay, there we go. And now that all of them contain a factor of row 0, that cancels out. So we get 1/2 L plus 1/3 K L squared over 1 plus 1/2 KL. Okay, and like I said earlier, K is going to have to be in units of inverse meters or 1/, meters. So that's going to be meters plus 1/, meters times meters squared is also meters. Good, so we've got meters plus meters over 1 plus 1/2. K is in 1/, meters times L is in meters. So the meters and meters cancel and the denominator is unitless. And there we go. So the units for this will be meters in the numerator divided by no units in the denominator. This is going to be in meters, which is exactly what I would expect for a position. I'm trying to calculate a position. I would expect it to be in meters or whatever length and or position units you want to use. Centimeters, millimeters, whatever is appropriate for the problem you have at hand. Okay, glad I figured that one out. That's one less thing I have to shunt away into a pinned comment, or worse yet, a secondary video. So that is center of mass. Now let's talk about finding moment of inertia. Let's talk about moment of inertia. What color do I want to use here? Let's use U. What about moment of inertia? So the way we did moment of inertia before, this is actually going to be very similar to what we're doing with center of mass. The way we did moment of inertia before is we did a sum. We defined moment of inertia as, for a bunch of point masses, we said it was just the sum of mr squared. So we would do m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and so on and so forth for however many point masses you have. But what if you need to take a sum of an infinite number of these point masses? In fact, we could just go ahead and use this same example, this rod with a linearly varying density, and figure out how on earth do we get the moment of inertia for an object like this. Well, we once again chop it into small pieces of mass dm, and we would say that their distance from the axis of rotation, let's say my axis of rotation is over here. Let's say this is my axis of rotation. We need to define one anytime we need to do moment of inertia, because the same object should have more than one moment of inertia, one for each axis of rotation that you choose. So for this axis of rotation starting over here, very simple example, what we would want to do is we would want to use tiny bits of the total mass, tiny changes to the running total mass, and actually use this r squared as the integrand. We would actually want the r squared to be our integrand this time. So we would say moment of inertia for an object that can't be modeled as just a bunch of individual point masses, we would say it's going to be the integral of r squared dm. We take a bunch of dm's, we figure out what their r's are, we square those r's, we multiply that squared r by that dm, move on to the next one, move on to the next one. There's basically an infinite number of them. That's an integral. So we integrate, it looks like, from x equals 0 to x equals L again. And r, I guess in this case r would actually just be equal to this L that I've defined, or x, whatever you want to call it. And so your dm, you've got different options depending on how you want to define your variables. You could call it rho dl, or you could call it rho dx if you would prefer to replace r squared with x squared, or you can call it rho dr and just redefine this from x equals 0 to r equals 0 and just say r goes from 0 to big L. Whatever you prefer, whatever makes the most sense to you. It's all interchangeable. So yeah, let's go ahead and actually do this one as a quick example. Well, I don't know about the quick part, but it's an example at the very least. So I'm going to go with this. I'm going to define dm as rho dr. So r squared, so it's going to be the integral from 0 to L of r squared times rho dr, where rho is equal to rho 0 times 1 plus kl. So that's going to be r squared times, integral from 0 to L of r squared times rho is rho 0 times 1 plus kl, or, well, I guess it won't be an L anymore. Since I've chosen this, I would actually define this as an R. L equals R in this case. dr. And then distribute the r squared. I'm going to factor out the rho 0 so that it doesn't give me problems like it did in the previous example. And then we have integral from 0 to L of, let's see, I would have an r squared and I would distribute it over 1 plus kr. So that's going to be r squared plus kr cubed, if I'm doing this right. R squared times 1, r squared times kr. Yep, dr. And then if we integrate this, pretty simple, r squared becomes 1/3 r cubed. Actually, let me do it all the way over here. Let me do it all the way over here so that I have the space to write some more stuff. What color do I want to use here? How about purple? So integral of r squared is going to be 1/3 r cubed. Of course, we have that rho 0 on the outside. 1/3 r cubed, and then kr cubed becomes kr to the 4 divided by 4, so that's plus 1/4 kr to the 4. Is that still visible on screen? Yes, it is. And then evaluate that from 0 to L, from r equals 0 to r equals L. That's going to be rho 0 times 1/3 L cubed plus 1/4 k L to the 4th minus rho 0 times 1/3 0 cubed plus 1/4 k 0 to the 4th. All of that is going to be 0. Conveniently enough. Don't just assume, by the way, don't just assume if your lower bound of an integral is 0, don't just assume that it's automatically going to be a 0. It depends on what function you get. If you integrate and you get a polynomial function, then yeah, in that case, you'll get a 0 when plugging in 0, but if you integrate and you get something like a sine function or a cosine function, cosine of 0, for example, is definitely not 0. If you get an exponential function, e to the 0 is not 0, it's 1. So be very careful about that. Be very careful about integration bounds being 0. It doesn't necessarily mean when you plug them in that you're still going to have a 0. Just slow and steady. Don't try to take too many shortcuts. You might end up walking into very dangerous pitfalls if you do that. So yeah, rho 0 times 1/3 L cubed plus 1/4 kl to the 4th is going to be the expression for the moment of inertia of this thing. So let's check the units, because we're supposed to get kilogram meters squared, or mass units times length units squared, to be more general about it. So that's going to be mass per length. Mass per length times length cubed is mass length squared, so that's going to work out. And then what about this? We said the k is going to be 1 over length units. 1 over length units times length units to the 4th is length units cubed. Length units cubed times mass per length is going to be mass times length units squared. So yes, it will be in kilogram meters squared, or whatever version of mass and length units you want to use. So this checks out. All right, for other integrals, if you want to do the integral of just like a rod or a stick of uniform density, you should be able to do it. The uniform density is really simple to define. You would just do, if your object has uniform density, then you would say your density function would be the total mass divided by the total length or area or volume, depending on how many dimensions you're working in. For a rod, length is appropriate. If you were trying to do like the moment of inertia of a solid sphere, you would use a volume density. So just define it as the total mass divided by the total length, total area, or total volume, depending on what is appropriate for your scenario, and use that as your density function. Your dm will be density times dl, if it's length, dA, if it's area, dV, if it's volume. If you want to see some other examples of me deriving the moment of inertia formulas for some of the familiar shapes that we've dealt with before, if you were wondering where those formulas came from, well, one, I would recommend you try and figure out how to do them on your own. But apart from that, if you haven't seen them already, I've done a few examples of those derivations in my Riemann sums videos that I referred to 2 streams ago, and which I will probably link in the iCard in the top right corner of the video once I actually get around to reviewing the video. I haven't actually gotten to do that yet for the past 2 streams, so I'll probably get that done at or shortly after this coming weekend, somewhere around that time. So I would hope I would get it all done by, let me think, what's a day that I would have some time to actually get that done? Probably somewhere around Wednesday or Thursday of next week. So yeah, come back in a week if you want to see the things that I've been saying I wanted to do in post. Pinned comments with corrections and links and all that. But otherwise, just go to the live tab on my YouTube channel and look for, it was from, I want to say it's like September, October-ish, 2 videos with the term Riemann sums in the title. Across those 2 videos, you should find some examples if you do some digging around. Anyway, now that we've gotten the calculus definition of center of mass and moment of inertia out of the way, what else do we need to do for rotational dynamics? Let's cross those 2 out since they're done. How are we doing on time? 3.5 hours. And how am I doing over here? Okay, we might actually get this done in under 6 hours. That would be nice. Oh, parallel axis theorem. Okay. Proof of the parallel axis theorem is next. Now that we've actually derived how to do moment of inertia, let's say I have some weird shaped blob of an object, and let's say its center of mass is somewhere, let's say its center of mass is over here. and we originally have it rotating about an axis through its center of mass, but then we decide, you know what, I want to rotate this thing through another axis parallel to this original axis. Let's say that new axis is over here. And let's say that these two axes are a distance d apart. Let's say those two axes are a distance d apart. How does the moment of inertia around this new axis relate to the moment of inertia around the old axis? Well, first off, I'm going to say, in the plane of this object, I'm going to say that this, I'm going to call this my x-axis. I'm going to call that my x-axis, and then that would then mean that my y-axis, think of this in 3 dimensions. That would mean my y-axis is something like that. And yeah, some of this blob is going to be like, how would I say this? So basically, I'm saying that my x-axis is going to be something like this, my y-axis is going to be like that, but I have it kind of slanted because I'm trying to illustrate that this picture is supposed to be kind of 3D going behind the page, if that makes any sense. So what I can do here is I can say that the moment of inertia about the old axis, or actually wait, no. I want to do moment of inertia around the new axis. That's going to be the integral of r new squared dm. And r would be, let's see, so in general, the definition of r, if I were to take a random piece of this thing, let's say I were to take this piece over here, take this small chunk over here, and call that my dm, then this distance over here would be r, and r is actually equal to x squared plus y squared, right? If you were to draw a right triangle over here, one side of this triangle is going to be whatever this x is, the other side is going to be, well, however far you are along the y-axis. So r new squared is equal to x new squared plus y new squared. Well, my choice of axis, I decided to call this the x-axis so that I could make a simplification. There is no new y. We haven't moved in y from the original axis. So the original axis of rotation going through the center of mass, we moved along a direction, and I chose to make my x-axis along that direction so that we wouldn't have any change in y to consider. I could have just used this as my x-axis, and then we would have had to worry about the y. But why would you do that when you can always just choose to define your x-axis to be the axis along which the rotation axis has been moved compared to the original rotation axis? It's just easier to define your x-axis to be an axis that both of these rotation axes go through. It simplifies the math. So y nu squared is actually not going to be different from the old y. Whatever y this was at, you're at the same y here. So y nu squared is actually equal to y old squared. So what about x nu squared? Well, the new x is going to be, if the old x was over here, x center of mass, the new x center of mass, plus the distance d. It would be plus a distance d away. So that's my x nu squared. Let me think here. Yeah, my new x position is going to be equal to the old x position plus we moved a distance positive d in the x direction. I could have drawn this the other way around, where my y-axis goes through here, in which case... No, wait a minute. What I mean to say is, I could have gone the other way around, as in this distance d. Yeah, I could have done a situation where this distance d is in the opposite direction to the left, in which case this would have been x center of mass minus d for x nu. It's actually not going to matter. Once we get all the math done, we're going to see that it's not actually going to matter. But that's x nu squared plus y nu squared is y old squared. It's y center of mass squared. So that's your r nu squared redefined. So let's go ahead and write that up in here. So we have, if I square this, I get x center of mass squared plus 2x center of mass d plus d squared. That's what I get from foiling this term. And then plus y center of mass squared. And then all that times dm. Well, one thing I can always do with integrals and derivatives is separate them into sums and differences. I can always separate them into sums and differences. So I'm going to go ahead and take x center of mass squared plus y center of mass squared and put them in their own integral. I'm going to take this 2xd and put that in its own integral, and I'm going to take this d squared and put it in yet another integral. So I'm going to split this into 3 separate integrals. So I'm going to have x center of mass squared plus y center of mass squared dm plus integral of 2x center of mass d dm plus a third integral of d squared dm. Okay, x center of mass plus y center of mass, or rather x squared plus y squared of the center of mass, that's just r of the center of mass. As for this over here, I'm going to factor out the 2 and the d. And then I get the integral of x center of mass dm. And then over here, this is just going to be the integral of d squared dm. I'll just keep it as an integral for now. Okay, integral of r center of mass squared dm. Well, that would just be the definition of the moment of inertia about an axis through the center of mass. So that's just I center of mass. Okay, what about this? This integral over here, the integral of x dm, what is that? What is that? The integral of x dm. That would be at least the numerator part of the definition of center of mass. That would be the numerator part of the definition of center of mass, which, let me see, that's supposed to be 0, but I'm blanking on the justification. This is supposed to be 0, and the reason is because I defined my x-axis over here. My x center of mass I've defined as being 0. Okay, so that's why that's 0. So this whole term is gone. So that's plus a 0. And then plus the integral of d squared dm. Well, d squared is a constant, and then the integral of dm is just going to be the total mass, m. So that's going to be md squared. And there you go. We have the parallel axis theorem. The moment of inertia about the new axis equals the moment of inertia about the center of mass plus the mass of the object times the square of the distance between the center of mass axis and the new parallel axis. So that's proof of the parallel axis theorem, in case you weren't completely sold on it before. And now we can cross that off the checklist. I think I might be coming down with something. Here's hoping I don't wake up sick tomorrow. Or worse yet, go to bed feeling sick. Let's see, according to my list, we've got... Okay, so here's another thing. Now this is actually going to be a really quick one. Pick a color. I guess we haven't used orange much today. Okay, so some of you might remember there was a problem that we did in the rotational dynamics chapter where we were trying to calculate the work done by a force, and we, instead of using force and displacement, we were looking at a rotating object. We were looking at a force that was causing an object to rotate. And we came up with an equation where we proved that torque times delta theta is equal to the change in rotational kinetic energy. Is equal to the change in rotational kinetic energy. So we can go over that again real quick. If you substitute the torque with I alpha, and then you use the third equation of kinematics, rotational kinematics, then you would have omega final squared equals omega initial squared plus 2 alpha delta theta. Subtract omega initial squared and divide by 2, or multiply by 1/2 is what I will do. And you have 1/2 omega final squared minus omega initial squared is equal to alpha delta theta. So if I go ahead and make that substitution in here, then I get, I'll pull the 1/2 out front, 1/2 times copy over the I, And then for the rest of alpha delta theta, you would just have the omega final squared minus omega initial squared. And if you distribute the 1/2 I, you get 1/2 I omega final squared minus 1/2 I omega initial squared. That is equal to the change in rotational kinetic energy, which would also be the total work done by that torque, assuming that there's no change in translational kinetic energy to take into account. Assuming that the only kinetic energy change is rotational, this would be all of the work. So yeah, work done by a torque is torque times delta theta. Well, there's an integral version of this equation. So if you have a variable torque, then you can imagine if the torque varies with the angle through which the object has already been rotated, you can imagine that this multiplication just turns into an integral of torque as a function of theta times d theta. This is not too different from the work equals F as a function of x dx, or F of r dr, if you want to be more general about it. You probably aren't going to need to use this, but now you know, just in case it pops up. There might be a situation here or there where it might prove to be useful, but in my experience, it's not very common for the AP exam to give you anything that calls for the use of this, because, I mean, even the algebra version of it, you could just take the torque and calculate force from it, and then use the arc length as a distance, and you could rewrite this as an F delta x. But in college physics, you might come across some proofs at the very least that might require the use of this integral. So just food for thought there. Just something that might occasionally come in handy. I don't know why I wrote this one. The integral of angular acceleration with respect to time. That's just angular speed. Oh, I think I wrote it as like a placeholder to remind me to do just all three of the rotational kinematics variables. Okay, yeah, that's already taken care of. Then that leaves us with two more things involving angular momentum. So angular momentum. We did say for angular momentum that the change in angular momentum is equal to torque times change in time. This is just like how change in linear momentum is equal to force times change in time. Well, there's a calculus version of this, so if need be, if your torque is not constant, then you can say that your change in angular momentum is equal to the integral of torque as a function of time with respect to time. Or the other thing you could do is if you divide delta L by delta T, the other thing you could do is you could say delta L over delta T equals torque. And then if you don't have, well, I guess this would be average torque. And if you wanted instantaneous torque instead, you would just do dl dt. Instantaneous torque would be dl dt, derivative of angular momentum with respect to time. Could come in handy if you were given something like a graph of angular momentum versus time, and you were given some sort of curve and you were asked, what's going on with the torque at given points in time along this graph. You would just use the slope of the graph and justify it by saying torque is equal to dl dt. Or I guess you could also have the other version of it. You could have a graph of torque versus time and use area under that curve to calculate change in angular momentum. So that's two more equations out of the way, and that just leaves us with one more thing for simple harmonic motion, plus something in simple harmonic motion that actually connects with the shell theorems that we discussed earlier today. So let me go ahead and see what these problems I picked out are all about. Page 197 is the first set of them, so let's see what you have for me. Let's see. I marked these as not being on the AP, but I think I still wanted to do them, and I don't remember why. It says Newton's second law for rotation as net torque equals I alpha. Consider the case of a particle moving in the xy plane under the influence of a single force. And then it's got a multiple choice. I don't see why this would be marked as not being an AP problem. That being said, it's not a calculus problem, so it's not what we need to go over. Oh, wait, I'm looking at the wrong section. It's in the exercise section, not the multiple choice section. Okay, let's see. What do you have for me? Oh, okay, I see. So it's giving me some stuff in unit vector notation. Okay, and I was thinking of going over an example or two of calculating a cross product using determinants, but I think I will actually pass on that in the interest of time, especially since it's not something you're going to be expected to do on the AP exam. Okay, let's skip over to this one. It says a pulley having a rotational inertia of 1.14 times 10 to the negative 3 kilogram meters squared and a radius of 9.88 centimeters. Gonna need a new sheet for this. It says a pulley having rotational inertia 1.14 times 10 to the negative 3 and radius 9.88 centimeters is acted on by a force applied tangentially at its rim that varies in time as F equals AT plus BT squared, where A equals 0.496 newtons per second and B is 0.305 newtons per second squared. If the pulley was initially at rest, find its angular speed after 3.6 seconds. Okay, I think this one is simple enough. So, pulley with rotational inertia of 1.14 times 10 to the negative 3 kilogram meters squared. And radius 9.88 centimeters. R equals 9.88 centimeters, or 0.0988 if you convert it to meters. Acted on by a force, and the force is a function of time. It equals AT plus BT squared. A is 0.496. I don't know why they wouldn't just write it out up front. 0.496 T plus 0.305 T squared. And this will come out, the way they've defined it, it will come out in units of newtons, so we don't have to worry about that. If the pulley was initially at rest, so omega 0 equals 0, find its angular speed after 3.6 seconds. Find omega after 3.6 seconds is the question. Okay, this one should be pretty simple. I mean, the force is applied tangentially at its rim, so the torque would just be R times F times sine of 90 degrees, sine of 90 being equal to 1. Yeah, if I were to draw the pulley, you have some sort of force applied tangentially to it like this. Makes a 90-degree angle with this R. Yeah, pretty simple. If you multiply by R, then I guess this function turns into torque as a function of time. Equals, I'm just going to keep it as an R. You can plug in the number on your own. Oh, I just copied it over, didn't I? Hold on. Let's do this. Torque as a function of time equals R times force as a function of time. There we go. And then it said find its angular speed after 3.6 seconds. Well, torque is equal to I alpha, so we would want to find alpha would be our task here. So we would want to find alpha of t equals, let's see, I alpha is equal to torque, so torque over I is equal to alpha. So torque of time t divided by I would be alpha of t, and then just take the integral of alpha of t, whatever that is. You'll get something proportional to 0.496 over 2 times t squared, plus something proportional to 0.305 over 3 t cubed. And you'll have a plus c. You can solve for the c because they told you that at time 0, omega is equal to 0. And then once you have that, plug in time 3.6 and you're done. Yeah, okay, that's not too hard. I'll leave that to you guys. What else? What else? We've got 2 of those. Let's see what they're about. This one is saying, show that for an object that can rotate about the x, y, or z axis, it says show that moment of inertia about the x-axis plus moment of inertia about the y-axis plus moment of inertia about the z-axis is equal to 2 times the integral of r squared dm, where r is measured from the origin, not from the axis of rotation. Where r is measured from the origin and not from the axis of rotation. Okay, so if I were to just draw, I guess, a coordinate system, here's x, here's y, and here's z. Show that for an object that can rotate about the x, y, or z axis, that sum is equal to 2 times the integral of r squared dm, where r is measured from the origin, not from the axis of rotation. Okay, so I guess I need to draw myself some sort of random object. Let's say some sort of blob that has some dimensionality to it. Yeah, some sort of 3D blob-like object. Just random thing of random shape and size. So, moment of inertia of this thing about the x-axis, y-axis, and z-axis. Well, I suppose I could just do, for its moment of it, I did this one in my head the other day, but I'm forgetting what it was that I did for this. I think it's really just a matter of what I am remembering is it was just a simple matter of understanding something about the geometry of it. It was, let me think. So you pick random points within this blob that are a distance r from the origin. So let's say I pick out this random piece over here. Let's say that's the dm that I choose, and that's my distance r from the origin. And then I'm going to drop a projection of this onto the xy plane like this, and then that's going to form a right triangle in 3D. And this over here, let me do it in a different color. How about green? This over here is yet another right triangle. So I guess I'm about to prove to you the statement that I gave 2 streams ago without proof. If this over here is the x-coordinate and this over here is the y-coordinate, then the hypotenuse of this triangle in the xy plane is going to be the square root of x squared plus y squared. So that's going to be this over here. Square root of x squared plus y squared, that's this over here. And then this thing over here, squared plus this squared, well, this is just z. So z squared plus this thing squared is just remove the square root from here. So if I add these two, I get x squared, or rather if I add the squares of these two, I get x squared plus y squared plus z squared is equal to r squared. So r squared is equal to x squared plus y squared plus z squared. So integral of r squared dm is equal to integral of x squared plus y squared plus z squared dm. And that's equal to integral of x squared dm plus integral of y squared dm plus integral of z squared dm. Integral of x squared dm, well, that would just be the moment of inertia about the x-axis. No, wait. Would it be? Hold on. Integral of x squared dm. No, actually. No, it wouldn't be. X is gonna be the distance from, okay, hold on. I think it's coming back to me. Rather, I want to group these two together. Okay, I want to group these two together and say that so this is going to be integral of x squared plus y squared dm. Oh, no. Okay, I've got it. So here's what you do. You do them two at a time. So moment of inertia about the x-axis, around the x-axis. If I use the x-axis as my axis of rotation, then the distances from the x-axis would be, let me draw a new coordinate system so that this is easier to see. So here's x, here's y, here's z. So if I take something like let's say I take like some sort of cylinder. I'm just drawing something simple for the sake of easy illustration, but it should work with any shape. Let's say I take something like a cylinder and I'm trying to define a distance from the x-axis. Then distance from the x-axis of a point on the surface of this cylinder, for example, would just be, well, I can take this, which is my y, and take this, which is my z, and then this distance squared would just be z squared plus y squared. So moment of inertia about the x-axis is distance from the axis squared dm integrated. It's going to be d squared dm, where d squared is going to be z squared plus y squared. It's going to be z squared plus y squared. Okay, and then similarly, moment of inertia about the y-axis would be the integral of, I guess we'll call that dx, I'll call this dy squared dm equals the integral of, if you just imagine rotating this picture and moving this cylinder, flipping it over to where it's around the y-axis, you can probably see that that is going to be x squared plus z squared. The distance from the y-axis squared is going to be x squared plus z squared dm, and then the distance from the z-axis squared is going to be x squared plus y squared dm, which I actually probably should have started with this, come to think of it. Yeah, that probably would have been better for me, but I wasn't thinking straight. Anyway, so if we add these together, ix plus iy plus iz, then what I'm going to have is a z squared and a z squared, so that's 2z squared, and a y squared and a y squared, that's 2y squared, and an x squared and an x squared, that's 2x squared. So I have two of each. So I have ix plus iy plus iz equals 2 of the integral of x squared dm plus 2 of the integral of y squared dm plus 2 of the integral of z squared dm. Which is 2 times the integral of r squared dm, which is 2 times the integral of r squared dm. There we go. Okay, and apart from that, we have, let's see, in this problem we seek to compute the rotational inertia of a disk of mass m and radius r about an axis through its center and perpendicular to its surface. Consider a mass element dm in the shape of a ring of radius r and width dr. What is the mass dm of this element expressed as a fraction of the total mass m of the disk? What is the rotational inertia? This is an example of calculating the moment of inertia formula for an object. I have examples of those in my Riemann sum videos, so you can go look at those. And if you don't like my videos, you can always go look at somebody else's videos. All you'd have to do is just type derivation of moment of inertia for solid sphere or whatever object you're interested in. And chances are somebody on YouTube has done it. Okay, so that leaves us with a couple of angular momentum stuff. A couple of angular momentum questions, and then we'll talk really quickly about the one place where calculus applies to simple harmonic motion, at least as far as AP students are concerned. And then we'll do the planetary pendulum, and then we will call it a day there. So I'm now moving to page 221. Here we are. And it looks like I have 2 multiple choice questions highlighted. What were you about? Okay, so this one says, particle moves with position given by, so a particle moves with position given by r of t equals 3t I hat, so position in x direction is not constant, plus 4j hat, where r is measured in meters when t is measured in seconds. For each of the following, consider only t greater than 0, only positive time. So first it says the magnitude of the linear velocity of this particle is increasing in time, constant in time, decreasing in time, or undefined. The magnitude of the linear velocity. Well, I would just take the derivative of this once, and if I take the derivative, then I get v of t equals the derivative of 3t is just 3, and the derivative of 4 is 0, so yeah, it only has a velocity in the x direction. So it's constant. Next, it's asking the magnitude of the linear momentum of this particle. The magnitude of the linear momentum is increasing, decreasing, constant, or undefined. Well, they didn't say anything about its mass changing, so I'm assuming it's got a constant mass, like most objects would. And if the mass is staying the same and the velocity is constant, then the momentum is constant. The linear momentum must be constant. Okay, next it's asking the magnitude of the angular velocity of this particle around the origin. Is it increasing in time, decreasing, constant, or undefined? The angular velocity. So let's go ahead and actually draw this thing. So it starts, here's x, here's y. It starts at, when t equals 0, it's 0, 4. It starts at 0, 4. Let me use a darker color. Let's use this one. It starts at 0, 4. So let's say 4 is over here. So it starts here, and it moves in the positive x direction. So it moves like this. And it's saying that the angular speed of this thing about the origin is increasing, constant, decreasing, or undefined. Well, when it's over here at the very beginning, I imagine that is where its angular speed would be the greatest. Because when you're moving from here to, yeah, so a bit of a crude explanation, but if you move from here to here, then your delta theta is, well, this. But after some time passes, if you're moving, say, from here to here, it should be the same size step in the same amount of time. This delta theta over here is even smaller than whatever this is. And you can imagine after a long amount of time has passed, if you again move for, let's say, 1 unit of time, then I don't even know if this is gonna, yeah, this is not gonna show up really nicely, but great. Yeah, I'm messing up the drawing, but I think you guys are seeing my point. This theta is even smaller, so the rate of change of theta with time is decreasing. The angular speed is getting smaller as you get further and further away as more time passes. So I would say that the magnitude of angular velocity about the origin is decreasing in time. If I wanted to prove this more mathematically, then I guess I would have to define, let me see, I guess I would have to figure out like at what angle it is with the origin, and then use that to define components, one perpendicular to the distance from the origin, and one that's parallel to it, and then I would just look at that perpendicular component of the velocity and divide it by the distance from the origin and define that as my omega. At least that would be my initial thought on how to tackle this if I were to try and prove it analytically. But I think just arguing conceptually, doing this, while crude, I think it's a lot quicker than trying to do all that math. So definitely, especially for multiple choice, if the analytical approach is too time consuming, I would just go for something simple like this. And then last question for this particle, it says the magnitude of the angular momentum of this particle about the origin. Is it increasing, decreasing, constant, or undefined? So for an object moving in a straight line, we've been over this before. For an object moving in a straight line, angular momentum is going to be r cross p. And the magnitude of that is going to be, r times p times sine of theta. We already said that the magnitude of the linear momentum is constant. R is changing, but what about r sine theta? So so theta is going to be the angle between, is going to be the angle between the r and p vectors. So p is always going to be to the right. R, let's say at this point, for example, r is this way, and p is this way. And if I do r sine theta, theta would just be, well, you could use this angle over here. Hold on, let me draw it a little bit better. So I'm gonna, let's say I do it for this point. Let's say I do it for this point over here. So I'm gonna say, when you're at this point, you've got a momentum in this direction, you've got an r in this direction, and then for theta, you could use this as the angle, or you could use this as the angle. Either one is fine because sine of this smaller angle is equal to sine of this larger angle as long as they add up to 180 degrees. I'm going to use this. So sine of this angle, I'm going to say this is my theta. If I do r times sine of theta, what's that going to be? Well, it's going to be this. If I complete a right triangle over here, this is going to be r sine theta. So if I pick a different r, say over here, and my momentum is still in that same direction, I'm going to have a new theta over here, and r times sine of this new theta, oh, it's going to be that same amount. It's just going to be 4 in this case, right? Why was it 4? So r sine theta is always equal to 4. So r sine theta is constant times magnitude of the momentum is constant. The angular momentum magnitude must also be constant. So that was more just a bit of an exercise involving unit vector notation, although it didn't really change the problem much. But there you go, you got to see it one more time. What about this one? It says a particle moves with constant momentum, p equals 10 I hat, and yeah, that's it, just 10 I hat, 10 in the positive x direction, 10 kilogram meters per second. The particle has an angular momentum about the origin of L equals 20 kilogram meters squared per second, k hat, when t equals 0. The fact that it's a k hat, that it's in the z direction, like I said earlier, not something you need to know for the AP exam. They'll just focus on clockwise versus counterclockwise. You don't need to worry about this definition of direction for things like angular momentum and torque being in the positive or negative z direction for an object that's in the plane of your page. So I wouldn't worry about that too much. But yeah, we've got a momentum, a linear momentum of 10. Don't want to use that. Let's use purple. So we have a linear momentum of 10 kilogram meters per second in the x direction, and an angular momentum of 20 kilogram meters squared per second in the z direction, which just means it's counterclockwise as far as we're concerned. And that is when t equals 0. So it's got two questions. First question is the magnitude of the angular momentum of this particle is increasing, decreasing, constant, or possibly but not necessarily constant. They did say that the linear momentum is constant. They did say the linear momentum is constant, while the angular momentum, all they said is that it starts at this value at time 0. So the magnitude of the angular momentum of this particle, is it increasing, decreasing, constant, or possibly but not necessarily constant? How much do we actually know about this particle? Let's see what I can draw for this. So we would have, we know that the particle is moving in a horizontal direction, or that it has, yeah, it's moving in a horizontal direction because its momentum is constant and in the positive horizontal direction. We know that. And we also know that its angular momentum is clockwise based on the fact that it's in the positive k hat direction. We know that it's clockwise, so that tells me that the axis of rotation that we're using to define our angular momentum must be somewhere up here above this thing. So let's say, for example, it's over here. Just some random place above this thing. Okay, so this thing is going to move along this line, and our axis goes through here. Yeah, no matter how I slice it, the r sine theta, just like in the previous problem, is going to be constant. This thing over here, this is going to be the r sine theta, and it's got to be constant. If we know for a fact that our axis of rotation is perpendicular to the page, which we do because of, well, actually, let me think. Do we, though? We know that at one moment in time, the angular momentum, well, they can't just change the axis no matter how much time passes. Okay, yeah, I'm convinced the angular momentum would have to be constant. Because no matter where this particle moves to or from, as long as it's moving in a straight line, whatever you defined as this axis here, if it was an axis that was, you know, tilted or something like that in such a way that this object could get closer to or farther from this pivot point, whatever you want to call it, this axis position, then we'd have a reason to believe that the angular momentum is changing, but we know that the axis, rather, we know from looking at the way this angular momentum is defined at time 0, we know that the axis is perpendicular to the page. So yeah, you're going to be at a constant r sine theta away from the line of motion of this particle. So yeah, the magnitude of the angular momentum of the particle is constant. And then the second question is the trajectory of this particle. Does it definitely pass through the origin, might pass through the origin, will not pass through the origin? But it is uncertain how close it will pass to the origin, or will not pass through the origin, but one can calculate exactly how close it will pass to the origin. Well, we can look at the magnitudes to figure that out. So at closest approach, r sine theta would give me, so when we're closest, right over here, angular momentum, r sine theta would just be r. And at closest approach, that would mean r times p, r times 10 is equal to 20, which tells me that r equals 2. So the closest we can get to this axis of rotation, is 2 meters. R sine theta is 2 meters. Oh, and come to think of it, it says the particle has an angular momentum about the origin of 20 kilogram meters squared per second k hat. So it's already through the origin. So actually what I should have drawn is take all this and move it down to here. What I should have drawn is axis of rotation here, and then my momentum I would have to draw like over here. This would be the line of motion. And yeah, in that case, it's not going to go through the origin because it has no way to move in the y direction. Well, yeah. It has no way of going through the origin because it can't move in the y direction. It's going to just continue moving parallel to the x-axis. But we do know for a fact that it can get as close as 2 meters to the origin. That's the closest it can get. So it would be the last choice. Will not pass through the origin, but one can calculate exactly how close it will pass to the origin. All right, there's that one taken care of. And then in the exercises, there was one that I marked with a star. Why did I mark it with a star? Ah. I see. Well, I mean, we already talked about it earlier, but it is reminding me of something I forgot to do. So this over here, another name for this delta L equals an integral of torque with respect to time. As you can imagine, this is called angular impulse. I think I may have brought it up way back in the rotational dynamics stream where this topic specifically was brought up, but just in case I didn't, yeah, this is called angular impulse. Delta L is equal to angular impulse, the same way that delta P is equal to impulse. So yeah, there we go. So yeah, I don't need to do this problem. I think it was just one of those problems that I listed because I wanted to use it as a way to remind myself to point that out. And point it out I did, so we are ready to talk about the last couple of things and then we will wrap this up. Maybe I can get this done in under 5 hours. And here I thought that 3.5 hours would be the upper limit of how long this would go. Boy, was I wrong. Okay, so for simple harmonic motion, really the only calculus you need is the ability to recognize the following differential equation. So if I do just my classic, horizontal spring problem, and it also works for pendulums and other oscillating objects that move with simple harmonic motion. We know that the net force acting on this thing is going to be force equals negative kx. And if we know that this is equal to the net force, then we know that MA is equal to negative kx. But we also know that acceleration is the second derivative of position. So if I divide by m, I get acceleration equals negative k over m x, and I can rewrite the acceleration as the second derivative of position. If I take the derivative of position once, then I get a velocity. If I take the derivative again, I get acceleration. So this is the second derivative of position equals negative k over m times x. I guess you might find it written in a more condensed form, so you could also see it written as dx, or d squared x rather, dt squared. just having this x moved into the numerator of this derivative operator, equals negative, I'm just going to call it c times x, negative constant times x. So if we see this, then you don't need to know how to solve differential equations. This is not some sort of separable differential equation you can do, but just whenever you see something of this format, second derivative equals negative constant or ratio of constants or whatever times your variable. Whenever you see this, second derivative equals negative constant times the variable, then you know that the solution to this is either x equals something times cosine, that something being the amplitude, something times some sort of cosine, and of course it could be plus or minus, or x equals plus or minus amplitude times sine of omega t. These are the only two solutions you should consider. What is this equation telling us? Something that we differentiate twice equals that same thing times a negative constant. Sine and cosine are the only functions we know that behave this way. Sine and cosine are the only functions that behave this way. If you take the derivative of sine twice, if you take the derivative of sine, or rather a sine, because there could be a constant out here, if you take the derivative of a sine of omega t, if you take the derivative of this thing twice, then what you get is, well, you take the derivative the first time, and you get a times omega because of the chain rule, doing that ahead of time, and then times cosine. And then we want to take the derivative of that. And if we take the derivative of cosine, that's where the negative comes from. So we get, let's see, chain rule again, so you get another omega, so that gives you a times omega squared. And then derivative of cosine gives us a sine in addition to that negative. Okay, so that's what happens if you differentiate sine twice. What if you differentiate cosine twice? Well, same thing. Only difference is if you start with cosine, you get the negative in the first step. If you start with sine, you get the negative in the second step. But either way, as long as you take two steps, you change back to whatever trig function you started with, and by the time you have changed back, you will have gotten a negative sign somewhere along the way, either in the first or the second step, but not both. So taking the second derivative of a constant times cosine of omega t, and come to think of it, there should also be a plus phi in here. So my mistake not including that to be completely general. There should have been a plus phi in both of these. But yeah, if you differentiate a cosine twice, then first time you differentiate, you get a negative. And that becomes a sine. And of course, we're taking the derivative of that. I completely forgot it. And taking the derivative again, we get negative a omega squared cosine omega t, or omega t plus phi if you thought ahead of me and remembered to actually include this. And then of course you can take the a cosine omega t here and say that that's going to be equal to your x if, well, hold on, let me let me not get too far ahead of myself here. So if I differentiate x twice, if I use cosine, if I use x equals a cosine omega t plus phi, then differentiating twice, I would get this over here. So I would either get, for my d squared x dt squared equals negative c times x, I would either get second derivative of a sine, which would be negative a omega squared sine omega t plus phi equals negative c times x, which is a sine. So if I choose x equals a sine of omega t plus phi, then this is what I end up with. Or if I choose x equals a cosine, I would end up with negative a omega squared cosine omega t plus phi equals negative c times, again the choice was x equals a cosine omega t plus phi. Or you also could have chosen x equals negative a sine and negative a cosine, in which case same thing. The only difference is instead of getting a negative here, the negative sign would be over here. So these negatives cancel and the a's cancel and the trig functions cancel. Let me actually switch colors for this. So the a's cancel on both sides of that equation, and they cancel on both sides of that equation. Sine omega t plus phi cancels with sine omega t plus phi. Same thing with the cosine version. So no matter which version you choose, you end up with omega squared equals whatever this constant is. Omega squared equals whatever this constant is. And for our case, for the spring case, the c is going to be this k over m. So omega squared equals k over m, and omega equals, we've seen this so many times in the simple harmonic motion stream, omega equals square root k over m. Basically, what you want to take away from this is, for anything involving simple harmonic motion, if you get acceleration equals negative constant times position, whether your position symbol is an x or a theta or whatever, if you get acceleration equals negative constant times position, then that constant, the square root of that constant, is going to be the angular frequency of the simple harmonic motion that ensues. That is all you need to know. You don't actually need to know how to solve a second order differential equation, although, I mean, it does help to just know that, you know, it helps knowing the intuition behind the two possible solutions, or I guess four if you count the plus and minus. It does help to know that these are the solutions and understanding why it makes sense that these would be the solutions. So maybe a bit overkill, but could end up helping you in future courses. But as far as the AP exam is concerned, though, they might give you some weird problem with some new kind of force that you've never seen before. They'll give you an equation for it, and you'll do some math with it, and then you'll get, actually, you might get something like, you might get something really weird where multiple forces are involved to cause simple harmonic motion. So you might have something where you get MA equals, and then you have multiple forces here, and they all have an X in common. And I guess you can factor out a negative, and there'll be like force 1 and force 2 or whatever. And maybe minus a force 3, and they all have an X in them that gets factored out. And then whatever this F1 plus F2 plus or minus F3 business is, whatever that is, after you divide it by m and take the square root, that's your omega for that simple harmonic motion. They might give you something like that, simple harmonic motion caused by a combination of forces. All you need to be able to do is recognize when you get acceleration equals a negative constant times x, or a negative, I guess, sum or difference of constants. All you need to be able to recognize is that the square root of whatever that constant stuff in front of the x is will be your angular frequency. And then from there, I would hope you remember that omega equals 2 pi times the regular frequency, or 2 pi over the period, and then use that to answer whatever questions they ask you from that point forward. And that's all the calculus you need for simple harmonic motion. They might give you something where they tell you to set up but do not solve a differential equation. So they might give you something like, let me grab, what color do I want? Let's use U. They might give you something like, again, an oscillating spring system, but there's friction, or maybe there's air resistance. And then you would say, okay, my net force, MA, is going to be equal to the spring force plus my air resistance. And here, if you end up with an equation that looks like this, v is the first derivative of x, so you would just rewrite it as dx dt. And this is a differential equation, but it's not a differential equation that you're expected to know how to solve. It's not a differential equation you would be expected to solve. If they asked you something like this, the furthest they would go is tell you, write but do not solve a differential equation that can be used to describe the motion of this object. And this would be like a damped oscillation problem anyway. It wouldn't be simple harmonic motion anymore due to having some sort of resistive or friction force that violates the conservation of energy requirement for simple harmonic motion. But yeah, if you want to learn more about this, then wait until college, I guess. Or you don't have to wait. There's always YouTube University. If you want to find somebody going over that stuff on a YouTube channel somewhere, I'm sure there are plenty of people who've already done it. Maybe take the first few weeks of a differential equations course first, though. And for that, you're going to need some calculus under your belt. So finish calculus, then maybe look at Khan Academy's differential equations, or whoever you prefer if you don't like Khan Academy. If you really want to learn how to solve this thing, I think it ends up being what? Some sort of exponential function, if I'm not mistaken. It's been a while since I've done these. That might be on my summer review list, differential equations. I should probably start offering that course. Maybe if I start teaching it more, I won't forget it so often. Okay, so that is done, that is done, that is done. Last thing on our agenda, and then we will call it a day. The Planetary Pendulum. The Planetary Pendulum, and I can probably fit it over here because we've already done most of the work. So the Planetary Pendulum, basically, the age-old question that a lot of people like to ask about what would happen if you drill a hole through the Earth all the way from one side of the planet to the other side of the planet, and then you drop something inside there. What would happen? Well, if we assume the effect of removing mass from this place is negligible, then we can just say that the force at any point within this hole, let's say I measure position from the center, so at any given time I'm going to be some distance, we'll call it little r, from the center. Sometimes r is going to be up here in the positive direction, sometimes r is going to be down in the negative direction. This thing is going to keep on going down and up and down and up, and I guess down and up is relative because people living on this side of the planet will say the exact opposite about which way is up versus down. But anyway, what is the force that's causing this motion? I'm already implying that this is going to be simple harmonic motion, so let's see if the force is going to have the format of something like the spring force. If it's going to have the format of F equals negative constant times, in this case, our position variable is r. Can I get F equal to some negative constant times r? Well, the negative part is going to be easy. We already know the direction of the force of gravity. If you're above this central point, it's going to be down, and if you're below this central point, it's going to be up. So the negative sign is already taken care of. Force gravity. We've already got the negative sign taken care of. Now we need to see if it's linear in r. So if we go back to, was it this page? I think it was this one. Yeah, over here. You might remember earlier today we said that within Earth's core, so we calculated what the acceleration due to gravity would be right on the surface of Earth's core, and then we calculated what happens if you go deeper into the core. And we said that once you go deeper, the acceleration due to gravity just becomes a linear relationship directly proportional to r. If we assume the entire Earth is of a uniform density, then we would end up deriving this same exact result. We would end up deriving the same exact result. So if you want to do the derivation, just follow the steps that we did back in that problem, and you will get the following result. You will get negative g mass of the Earth over the radius of the Earth cubed, all that is constant, of course, times the mass of the object, because we didn't have the mass of the object in that formula due to us having to find the acceleration, but here we want to find the force, so you multiply the mass of the object as well. Here we only have just the mass of the core, multiply by the mass of the object, little m, so that you actually have a force as a function of position instead of just an acceleration. So negative g mass of Earth, mass of object over radius of Earth cubed. all times r. This fits the bill. This is the format that we need for a restoring force, for a force that causes simple harmonic motion. And that's it. If you want to find the period and frequency of this motion, we can do omega equals the square root of this. Actually, wait. No, not the square root of this. It's the square root of this divided by the mass. Okay, so I guess we have to cancel out the mass anyway. Yeah. If this is going to be your net force, that's going to be ma, and then divide by m, so little m cancels out. So it's the square root of g, mass of Earth, over radius of Earth cubed. And then from there, multiply that by 2 pi to get your regular frequency, or take 2 pi divided by this to get the period of the oscillations, and have fun playing around in whatever space simulation game you have access to that allows you to drill holes through giant planets like this, and I don't know, leave a review depending on how physically accurate the games are. I think I had somebody, a friend of mine, tried that years ago when No Man's Sky first came out. I've never played that game, it's just not my type of game. But he did show a video where he was trying, at least, to dig a hole through a planet. I don't know if he ever actually managed to get all the way through the planet, or if the game even made it possible to begin with. But hey, maybe somebody will do it. Chances are somebody already has done it, if it is possible, and there's probably a video of it on YouTube. Maybe it was posted by that same friend of mine, for all I know. Anyway, that is it for today. In fact, that is it for the entire course. All we have left is a little bit of an overview for the exam. I'll have that planned for sometime this weekend, and I will find the earliest opportunity I can to timestamp this stream recording and the previous two. I need to get around to those and probably leave some pinned comments and notes on any mistakes or incomplete questions or things that I said I would post a comment for when and if applicable. So yeah, planning to get all that done by somewhere around next week, by like Wednesday, Thursday at the latest, I would hope. But if I can get it done even sooner, that is what I would prefer. Let me think. Any other closing comments? I'm not sure I have any other announcements. So yeah, hopefully this has been helpful. I didn't teach every single little thing, but I did try to be thorough where it mattered. And I would hope that most people who ended up viewing this series knew to also do their own practice and not just entirely rely on this to teach them everything. There's a lot that you don't learn unless you practice on your own and just throw yourself out there and do problems. And I know you've probably heard me ramble about this stuff throughout all the different streams on numerous occasions, but it doesn't hurt to remind one last time. Practice, practice, practice. The secret to being good at physics, it's not inborn genius, it's not genetics, it's really just sticking with it and continuing to learn and adjust your understanding. I wasn't anywhere near as good at physics as I am today when I took my AP Physics exam, and I still got a 5. And I can tell you, every year I'm still learning new things, even this year. If you were to ask my students about the number of times they asked me questions where I got stumped, and I told them, give me a week to think about this and I'll come back next week with an answer. Physics is something that you only master by continuing to do it. That is the secret. You just have to keep doing it. Other people will dump all their knowledge on the day of the exam and they will never think about it again, and in about 2 to 4 weeks they will forget everything for the rest of their lives. Don't let that be you. Even if you don't plan on specializing in something that's heavily physics focused, just remember these concepts as you interact with them on a day-to-day basis. Mechanics is very tangible. Mechanics is something that you just experience through every moment of every day. At the very least, remember these ideas conceptually. If not, if you don't remember like all the formulas and stuff, at the very least, remember conceptually how things work. Remember that when you increase this factor, this effect increases or decreases, as the case may be. And just in general, whether it's for physics or any other science, practice explaining things to yourself. When you see something happening, try to think through why it works the way it does. The more time you spend doing that stuff, the better you'll get at explaining. And being able to explain things well, whether it's in a science context or just in general, explaining instructions on how to do any random thing at work or at a community function or whatever, being able to explain things well. There are a lot of people out there in the world that are very bad at explaining, and maybe I'm one of them, who knows. But if you practice with it, if you start getting better at figuring out, if monitoring your words, figuring out how the way you word things might confuse people, if you can get better at trying to put yourself in the shoes of your listeners, then over time, you might not ever become the perfect explainer, but at the very least, you can increase the percentage of people that you don't have to re-explain things to. And I think that'll be a net positive for the world. Anyway, that's enough of me rambling. Hope you enjoyed the course, and hope you learned a lot. And I hope you got some sort of positive inspiration from this. That is it for tonight. Take care. Class dismissed.